Photo of skyline of city on water with image of cloud in middle, with rays projecting out to the edges of the photo. Figure 13.1 Business requirements determine cloud implementation and deployment strategies, creating an interconnected system that is based on selected application workloads, architecture patterns, and technologies. Credit. Modification of Cityscape by Raman Guy/Flickr. Public Domain Chapter Outline 13.1 Hybrid Multicloud Solutions and Cloud Mashups 13.2 Big Cloud IaaS Mainstream Capabilities 13.3 Big Cloud PaaS Mainstream Capabilities 13.4 Towards Intelligent Autonomous Networked Supersystems by combining different cloud systems or connecting a cloud node with a private network. Companies can develop solution architectures that give them all the benefits of clouds and allow them to scale applications without being tied down to one cloud vendor, which also ensures reliability and overall robustness. TechWorks is a startup company dedicated to leveraging innovative technologies as part of its repeatable business model and as a growth facilitator. Their vision is to develop next-generation secure, super society intelligent autonomous solutions. To achieve this, TechWorks needs a solution architecture that aligns with its goals while staying within budget. The company faces a choice between building and maintaining a local computing environment or utilizing third-party cloud services. Setting up a local environment requires a substantial initial investment dedicated to building and maintaining infrastructure. This option, while providing full access to develop, scale, and monitor their applications, was deemed too costly for TechWorks. Instead, TechWorks opted for a third-party cloud system to deploy and maintain their applications. By utilizing a cloud architecture, TechWorks benefits from virtual capabilities such as storage, networking, and computing without the heavy upfront costs. This approach helps TechWorks save on development costs while maintaining flexibility and scalability. However, cloud-based solutions come with trade-offs, including limited access and control over the provider's infrastructure, which may introduce vulnerabilities and dependencies. TechWorks needs to address several critical questions. How will they manage their budget to ensure effective application deployment and maintenance? How will they handle rapid growth in customer data traffic? What strategies will they employ to respond to data breaches and system maintenance? Before the widespread adoption of cloud computing, many large companies such as Samsung and IBM relied on extensive physical infrastructures, including multiple self-developed data centers. The advent of cloud technologies has transformed this landscape, enabling the virtualization of resources and presenting opportunities for companies to transition to cloud environments or hybrid models that combine cloud and physical servers. For new tech businesses without access to expensive local IT infrastructure, relying entirely on cloud resources is a common strategy. Choosing a well-designed cloud architecture is crucial for long-term cost savings, flexibility, scalability, and agility. Additionally, a secure cloud architecture can help mitigate potential cyber threats. For instance, relying on a single cloud infrastructure for development, servicing, and deployment exposes companies to significant risks in the event of a data breach. TechWorks decided to adopt a multi-cloud architecture, distributing responsibilities across different cloud systems for application communications, customer services, access control, and resource management. This approach enhances security and reduces dependency on a single provider. The previous chapter focused on cloud-native applications that leverage microservices-based architectures. In that case, individual workloads are implemented as services that may or may not reside on the cloud. In this chapter, we will explore how various cloud-based architectures are developed by combining specific infrastructure as a service, IaaS, and platform as a service, PaaS, capabilities and computing environments to accelerate the delivery of desired functionalities and benefits. We will also examine how TechWorks, as a startup, evaluates and implements cloud architectures to build solutions that meet their needs. Through examples utilizing cloud-based PaaS, such as IoT frameworks for temperature data collection and machine learning services for predictive analysis, we will demonstrate the profound impact of cloud deployment and workload implementation strategies on operational excellence and competitive advantage. Learning objectives. By the end of this section, you will be able to define and differentiate hybrid and multi-cloud infrastructure deployments, understand the importance of cloud mashups, understand how to accelerate the creation of solutions using cloud infrastructure and platform services. Cloud computing provides businesses with more options that help them deploy application workloads more effectively. Application workloads may include clients and servers in traditional client-server architectures, nodes in peer-to-peer P2P architectures, or services in microservice architectures. When it comes to cloud architecture, organizations need to determine which application workload should run in the cloud. Organizations taking advantage of cloud computing environments should ensure that it does not introduce delays in solution delivery and maintenance. Hybrid and multi-cloud solutions for large-scale applications, businesses look for better ways to manage users' inquiries without clogging a single cloud system. In this section, we will review different cloud solutions that are built upon combining a public cloud and a private cloud. Think it through. Cybersecurity and cloud-based architectures. Every year, organizations around the world are hit with major cyberattacks that affect millions and even billions of private accounts and records. To deter cyberattacks, organizations spend millions of dollars per year on cybersecurity. Cloud-based architectures are more difficult to secure and also partially rely on trusting security architectures provided by cloud service providers. In your opinion, why are organizations becoming more dependent on cloud computing, considering added security risks? Hybrid cloud solutions. One approach to managing cloud storage is to allow localization of infrastructure data while also utilizing third-party services for storing public data, hence implementations of hybrid cloud. Deployment of hybrid cloud infrastructures allows enterprises to manage flexible workloads using both public and private resources, opening the opportunity of having more management rights over sensitive data while also utilizing public clouds to deploy public applications. To accommodate a broad range of needs, hybrid cloud solutions aim for a dynamic environment by allowing a wide range of options to combat potential issues regarding different deployment, communications, and management. Several approaches that the hybrid cloud offers toward these issues include cloud deployment, application communications, and application and infrastructure management. Cloud deployment. When it comes to deployment, organizations look at the structure of their own application's architecture and decide how their features should be deployed among different layers of storage. They can choose to shift their features to the cloud and keep the system on-premise, or move a fraction of their deployed code to the cloud while keeping cold data or backups on their private infrastructure. Hybrid cloud systems unlock access to on-site backup, which protects organizations from major financial losses or downtime in case of a system failure or a data breach. This also allows easier access to data for a remote workforce, as the data are not tied to a single location. In addition, a shift of deployed code or data system onto the cloud allows corporations to automate application updates and maintenance or scale their applications accordingly, depending on peak times, to maximize efficiency. When using a hybrid cloud system, scaling up during peak times or when demand spikes means simply paying for more cloud resources instead of having to expand local infrastructure. Likewise, a company may have the option to downscale during slower times, enabling a company to pay for only the resources it needs when it needs them. Application communications. The main question when it comes to interconnecting one or several cloud and on-premises systems with varying providers and deployments is how to form effective communication between those systems. Businesses usually tackle the hybrid cloud network by implementing APIs as a means to communicate between different platforms, establishing secure network connections or VPNs to ensure dedicated protected connections, and encrypting data to mitigate data breaches. Note that the more complicated sets of systems the corporation manages require complex API architectures. Developers need to consider interoperability, data integration, and efficiency to design API systems that allow easy communication between systems while maximizing efficiency. Application and infrastructure management. With an interconnected web of cloud and on-premises systems, developers need to find a way to effectively monitor and keep up the performance of their resources. Because of the investment of multiple cloud systems from different providers, there will be different documentation and complex operational overheads. Developers need a way to simplify administration by centralizing control of all systems either through a unified tool, e.g., Azure Arc and Cloud Center Suite, or robust architecture. Ultimately, with a hybrid cloud system, the company has full control over its data and where they are housed, making it easier to make informed choices about data security. Careful planning of management for a hybrid cloud structure allows developers to easily control the scalability, flexibility, security, and cost of their hybrid system. The pros and cons of a hybrid cloud solution must be weighed against the needs and priorities of the organization that intends to use the solution. Typically, a hybrid cloud meets a broad range of needs, including flexibility and security, as follows: easier access to data to better support the remote workforce. The organization has the flexibility to provide remote employees with on-demand access to data that are not tied to one central location. Reduced costs. When demand spikes, the organization can avoid capital expenditures to expand its infrastructure and instead pay only for the cloud resources it uses. Improved scalability and control. Increased automation allows the organization to adjust its cloud settings to respond automatically to changes in demand, as well as optimize performance and efficiency, security and risk management. The organization has control over its data and improves its security by reducing the potential exposure of data. The organization can choose where to house its data and workloads, which makes it easier to implement security measures such as encryption, automation, access control, orchestration, and endpoint security. Industry spotlight leveraging hybrid cloud models for streaming. Hybrid cloud models are extremely common architectures for big consumer companies. Netflix, for example, in 2008, adopted the hybrid cloud model by combining on-premises database structures to store big movie files and then utilizing Amazon's simple storage service Amazon S3 to distribute data across cloud servers. They can manage their resources through built-in tools such as AWS Local Zones, which bring services closer geographically to a user. It is necessary for Netflix, as a streaming service provider, to adopt hybrid cloud models due to the amount of traffic and geography it covers on a daily basis, as well as to ensure users' smooth movie-watching experience. Multicloud solutions. Similar to hybrid cloud structures, a multi-cloud solution involves meshing several different computing environments to form a flexible working environment. Multicloud's main difference is that it is exclusively a combination of more than one public or private cloud system, compared to hybrid cloud, which is a combination of cloud and on-premises. The benefits of multi-cloud systems include automation and scalability, risk reduction, competitive pricing, and robust security. Automation and scalability. One of the cloud system's biggest advantages is the system's reliance on cloud infrastructure, which allows developers to effectively distribute workloads among infrastructures and leverage resources based on geographical patterns and peak usage time. In the long run, collecting data regarding the application's performance also allows complete automation in managing the multi-cloud infrastructure, which allows for convenience in controlling and optimizing the company's application. One of the reasons why cloud systems became increasingly popular over the years is because of the low cost of acquiring and maintaining cloud systems. With a multi-cloud system, an organization is motivated to shop around and choose multiple vendors for the best price. Different providers offer different services for different prices. There are enough cloud service providers today that an organization typically has many options to choose from. Risk reduction. By having access to multiple cloud vendors, the utilization of multi-cloud structures allows companies to maintain uptime in cases of data breach or system failure. If one vendor fails, the organization can switch to a different one. A vendor can also act as a complete backup in case the system needs a complete reboot. In a multi-cloud system, each cloud vendor manages its infrastructure. Services such as AWS and Azure offer access, keys, and secured network management. Multi-cloud architecture leverages this difference in security features between vendors to act as layers of a secured system, preventing a complete breakdown of the environment. Challenges of multi-cloud systems. With all the benefits that multi-cloud solutions offer, some challenges must be considered to mitigate risk and optimize the budget. Similar to hybrid cloud solutions, multi-cloud system networks can be hard to design due to the increasing complexity of the network as multiple cloud systems are connected. Furthermore, the complete reliance on cloud infrastructure requires dependence on the vendor's services and constraints, making it hard to unify systems or migrate workloads between different clouds. Organizations must consider these problems to mitigate risk and maximize profit when developing multi-cloud solutions. Typically, users rely on both hybrid and multi-cloud systems rather than selecting one over the other. Cloud mashups. A mashup typically describes a web-based application hybrid that combines features from two or more web sources to create a new service. These features communicate with the use of API, which are sets of protocols and tools that serve as a middleman between different software applications, allowing information to transfer between them. Cloud utilization allows complete virtualization of these multi-service web applications through vendors offering centralized tools and operations that support assembling and managing multiple sources, hence the emergence of cloud mashups. To understand cloud mashups, consider how news websites function. News providers typically get weather updates from Weathercom or other sites and gather other information, such as updates about stocks, shares, currency rates, and even additional news items from sites such as Reuters. The end product is a practical example of a mashup of multiple component parts. Cloud mashups have become increasingly popular over the years because of the plethora of public information that the service offers and the convenience of managing services completely through the cloud. Cloud mashups effectively allow developers to pick and combine different information from public sources and make their applications. It is extremely beneficial due to how much it enhances users' experience while promoting collaboration between services. However, due to its dependency on the API structure of the service, the discontinuation of a service can cause many applications to break down. This lack of scalability becomes a concern for cloud mashups, and constant upkeep is necessary for applications that depend on using public services as a means to collect and display information. Leveraging cloud services to implement cloud applications. Workloads hybrid multi-access computing ensures network scalability by introducing guidelines that constrain distributed applications to exhibit low latency and consume less power. This can be best achieved by locating and operating workloads at the mobile or network edge, which means maximizing communication performance between the local network or device. Endpoint onto the Internet. Products surrounding the IoT and computer infrastructures that rely on minimizing latency or collecting real-time data would benefit greatly from this. Furthermore, edge computing embedded in hybrid and multi-cloud models helps with encrypting data before sending them onto the cloud network, minimizing risks of data breach and complying with privacy regulations. Telecom services providers are slowly becoming cloud service providers in an effort to make cloud resources more readily available on demand at the edge of the network. To do so, they are implementing hybrid multi-access computing solutions and will eventually compete against or coordinate with the big cloud vendors. Businesses and individuals will leverage telecom service providers' edge cloud resources to develop bring your own cloud solutions. A bring your own cloud (BYOC) solution involves an organization allowing employees or users to freely decide on the cloud vendor that best suits their tasks rather than standardizing a single specific provider. Services such as Oz and Azure offer their edge-specific tools and frameworks to process data locally and deploy and manage edge devices for real-time analytics and machine learning. In the same way as Starbucks, as an example, plans to provide charging station services for electric cars shortly, it will also go beyond providing simple wireless access to its customers by being able to connect them to the cloud resources needed to operate cloud applications, e.g., extended reality applications that the store anchors to objects in the cloud. Looking at the near future, it is likely that the next generations of cloud-based solutions will evolve toward multi-access networking architecture. Note that this will not change the need for hybrid or multi-cloud workload deployment or the use of cloud infrastructure or platform services. What will change is which organizations will make these services available closer to the edge of the network to maximize performance and enhance users' experience. In fact, machine learning and large language models such as GPT and BARD may still need to be trained in remote big clouds depending on their resource requirements, but the resulting models will be moved and operated at the edge. This discussion highlights the need to understand how to leverage cloud infrastructure and platform services to support the development and operation of modern applications. In general, cloud services are available today via the big cloud portals, e.g., Portal AzureCom, and via software development kits (SDKs) or APIs readily accessible from pretty much any programming language used to develop cloud applications. In the next two sections, we will delve into the details of how to use these services practically to implement cloud applications. Learning objectives. By the end of this section, you will be able to learn how to use IaaS storage services, learn how to use IaaS compute services, understand IaaS support services for web and mobile applications, relate to IaaS container management services, understand IaaS support services for database management from a business model perspective. Startups and companies with fluctuating workloads depend on finding a way to effectively deploy and manage their applications. This includes considerations such as cheap, reliable performances that can adapt to unpredictable seasonal demands. This calls for a service model that allows businesses to access cloud resources and adopt agile infrastructures without having to worry about IT management. One solution to such demand is Infrastructure as a Service, IaaS. IaaS offers on-demand access to cloud computing services, provides a pay-as-you-go pricing model, and allows the user to take advantage of cloud servers by virtually managing data and servers for their application. IaaS allows the engineering team to optimize the platform from the infrastructure and does not get locked into any cloud provider's settings. In this section, we will delve deeper into the different layers of operations that IaaS provides. As the infrastructure is provided without any special setup, IaaS, as a framework, requires additional skills and time from the engineering team to set up and maintain their platform. Throughout these sections, we will go through different common infrastructures that mainstream IaaS providers usually accommodate so that we can determine the best approach to maintain our cloud applications. Storage service. A storage service is one of the base infrastructure components that a cloud provider would provide that allow the user and the application to read, write, and access storage. These services are elastic storage services, and the word elastic is used throughout the chapter to indicate an unlimited number of resources that the user can access from the cloud provider. Some common components in the application that may require storage access are analytical data, logging information, application data, images, and videos. The storage required for these components may grow over time as the application operates, so the users must understand the type of storage service that they choose for their application. It is also common that the user may choose more than one service to use in their application. There are several types of storage services that the user can choose from, depending on the cloud provider. For example, Microsoft Azure allows users to create a storage account that makes it possible for them to use blob storage as explained in the following paragraph. Mount Azure-based remote file systems to their local machine, create column-oriented database tables, or create a queue to receive streaming data from a sensor. However, there are three common types of services that all cloud providers provide. The first, file storage, manages data as files. This is the most common storage service among first-time users as it is the easiest concept to understand. Most users who use computers daily are familiar with file and the way it stores in their local environment. However, as file has a tendency to grow in size and its format can get complicated, the file storage becomes more difficult to manage as the application operates and grows in the cloud environment. The structure of the file system can also be carried into each file being stored in this service. Some common file metadata that are managed and tracked by the cloud provider are file name, file size, timestamp, and permissions. The second, object storage or blob storage, manages data as blobs with each blob representing any data format such as a file in a local file system. A blob can contain any type of data, such as a small value, a document, an image, a video, or a collection of such. Cloud providers allow access to the information stored and its associated metadata via an API SDK or via direct web links in the case of pictures, for example. Common metadata includes name, size, timestamp, and custom tag. In some cases, this approach helps manage the storage of items and also makes them available to anyone who is given access to them in the cloud, which is not possible when storing data items in a local file system. This service is commonly used by consumer applications and allows them to access and retrieve data items as objects, using their names and tags. The third, block storage, manages the data as blocks or physical range of storage in the physical device, such as a hard disk drive HDD or non-volatile memory express NVMe. Each block address can range from a few kilobytes or several megabytes in size. Because this service can provide a way for the user to directly access the data using a physical address, it does not need to manage the entire set of data objects. The most common usage for this service would be a system application such as an operating system or database where they need access to files much quicker, and they can keep track of and manage how the data are changed. To access the storage services from the application, the developer would have more than one way to access the data. Figure 13.2 shows a simple view of different access patterns on how the user and application can get access to the storage service. Graphic showing how admin, developer, user access Cloud API Gateway through console terminal, application, web UI controller console, and then to authentication authorization, storage access point and service interface and data device. Figure 13.2 as the diagram shows, users and applications can access storage service through different patterns, including CLI or command line interface. Attribution, copyright Rice University, OpenStax, under CC by 4 license. Most cloud providers will provide different tools to support different environments that the user may use to access their infrastructure and services. The storage service will usually be provided as a location in the cloud for the user to access. If the user is a developer, they can access the storage directly through their code using a software development kit, SDK, which is used to access the storage needed to read, write, and store data. This kit is usually provided by the cloud provider and works with different programming languages. Some applications running on the cloud environment also use this SDK to write operational data, such as logs, or consume different configurations that were stored in the cloud environment. If a user is a cloud administrator, they can also access the storage service through a computer terminal using command line interface, CLI. This is also a tool provided by the cloud provider, and this tool will allow users to access the storage service and manage their data. Finally, the user can also access the storage service through the web interface console through their browser. By doing it this way, the user can access their data interactively through their browser. Generally, cloud resources are available either via Cloud Portal Interface, an SDK that is accessed programmatically, or a CLI that enables users to invoke SDK constructs on the command line. Figure 13.3 shows the web interface for an Azure Storage Account Container (ACA) blob accessible via the Azure Object Storage Services web console. On the Amazon AWS cloud, blobs can be created as buckets within the Simple Storage Solution (S3). Screenshot of web interface for an Azure Storage Account Container (vblobs) accessible via the Azure Object Storage Services web console. Figure 13.3. This image from Azure Object Storage Services web console provides an additional example of the web interface used to store data containers, i.e., blobs in Azure within a storage account. Used with permission from Microsoft, another important component in the cloud storage service is the storage access point. The access point is one of the critical components in cloud architecture that will minimize the latency that the user can consume the data. Based on the user's location, the cloud provider can provide the available access point closest to the user's location to eliminate long I/O latency. However, this is also one of the key problems of leveraging storage service when the application is scaled out. Depending on the cloud provider, there are a fixed number of access points in an area for each account to consume. Usually, it would not be an issue for a small or medium performance application. However, for real-time and high-performance applications, this restriction may become a bottleneck for the application to operate correctly. This issue can be resolved when the user moves to a hybrid cloud solution where they can spend a bit more upfront to pay for backing up data devices and hardware that can be located in their local area. Compute services. The compute service provides the ability for the user to obtain access to a private computing environment and is another base infrastructure component that a cloud provider would need to provide. This is also one of the first things that the user will try when they start using cloud services. This will provide a similar experience to a remote computing service that a user may experience in their local environment. The user can access this environment to develop or run any tasks that they cannot run in their local environment. The performance of this service can vary based on the user request, or it can be based on how the application and tasks are required during runtime. Depending on the computer hardware specification, when they need to run, and how they scale based on the application requests, there are various services the user can select. The following are 3 common compute services the user can see from a cloud provider. A virtual compute service, VCS, which enables the user to request an environment to do some tasks and then shut it down to release the resource back to the cloud provider. Depending on when it was requested and how long the user keeps it running, the price for this service varies. A spot not urgent compute, which enables the user to get a task done, but keeps costs low by allowing the cloud provider to run the task without urgency when the time is convenient and cost-effective. A virtual functional and serverless compute service, which is an application that runs in the compute environment, is executed as a function and is then shut down when the task is completed. The user will get charged based on the number of tasks or requests that the service completes. Because this service requires a different backend service from the cloud provider to operate, the cost per time unit for this service will be higher than other services. This service is common for cloud microservice architectural applications, where the user may host different components and functions of their application as separate components. This will allow each component to be scaled independently and avoid a bottleneck to one large instance of an application needing to be maintained. Similar to storage service, the user can have more than one way to access compute service. However, because the user needs to interact with the compute service to complete a task, they usually access through 2 main channels, CLI and Web UI Controller Console. Figure 13.4 shows how different users, roles can access the compute service. Graphic showing how admin developer and user access Cloud API Gateway through Console Terminal or Web UI Controller Console, and then to Authentication Authorization, Compute Access Point and Virtual Compute Service Interface and Virtual Infrastructure. Figure 13.4. The access pattern for a compute service may differ depending. User's role, attribution, copyright Rice University, OpenStax under CC by 4 license. One thing to note is that we ignore the access pattern where either the user uses a local integrated development environment, IDE, to access the computing environment, or when the user accesses the IDE that is hosted in the virtual environment. In both cases, the user has to configure the computing environment differently to bypass the provided tools and interfaces. Another challenge in compute service that is similar to storage service is the limited number of access points in an area or cloud account that the user can use. However, this is not as big of a challenge as storage computing because most of the computing tasks can be scheduled, and it is easier to provide minimum compute service and operate with minimal performance that provides storage access with minimal I/O latency. The high I/O latency can destroy the user experience, and it can occur unpredictably. Linked to learning compute service is a critical component of cloud solutions. One of the largest providers of compute services is Amazon Web Services, AWS, which supports millions of customers, including small businesses as well as larger organizations. AWS's website provides an overview of compute and explains how these services benefit cloud computing. Web and mobile app services. Among all applications and workloads in the cloud, two common workloads have emerged in recent years. Those are web and mobile workloads, where the user wants to provide real-time access to all users across the globe. This is one of the most critical reasons why the user wants to move into the cloud environment, because the cost to scale the global infrastructure is extremely high. A content delivery network, CDN, is an important cloud capability that accelerates web and mobile workloads access globally. A CDN is a network of servers and associated networking infrastructure that is spread across the globe and allows access to web and mobile workloads from anywhere. It is configured to prioritize and cache common data and content, e.g., videos in different geographical areas, so it can increase access and processing speeds of mobile and web applications in the global network, which results in improved user experience and reduced energy costs. On-demand streaming services, e.g. Netflix, Hulu, Tubi, use CDNs to direct users to the closest server, i.e., a network edge server located at the edge of the network closer to their location from which they can stream their movies. The web clients apps provided by these vendors allow dynamic adaptive streaming over the web via the HTTP web protocol to ensure high-quality streaming of media content over the internet delivered from CDN servers. Figure 13.5 shows a high-level architecture of how CDN is set up on Azure Cloud Service. Illustration of users accessing Edge server from Origin server. Figure 13.5 Microsoft Learn's content delivery network on Azure Cloud Service is set up using a high-level architecture. Attribution. Copyright Rice University, OpenStax, under CC by 4 license outside of the infrastructure. The cloud provider is also providing other common patterns and services that most web and mobile applications need to use to provide an optimal experience to the end consumer. These patterns and services are pre-implemented and optimized by the cloud provider and have an easy integration with the compute and storage services where the application runs. The following are two common web and mobile cloud components. The component that stores and manages sensitive information securely while allowing the application to be scaled and deployed in different environments on the cloud is secret and configuration management. Different environments will require different configurations and secret details, such as database access or language settings. The best practice to handle complex environmental configurations and secrets is using a global cloud service to inject those details during runtime, so the application code can be free of custom implementation and the application deployment and version control would be much simpler. Most cloud providers will allow the user to manage their custom configuration and secrets and update them during application runtime. The component that allows developers to centralize all logging data and provide a comprehensive view of all events happening with an application at any moment is logging and monitoring management. As the application grows and scales in different environments, the ability for the developer to know and understand how their application runs becomes more and more important. The administrator's ability of the administrator to identify and mitigate the issue during the runtime is an essential requirement for any cloud-based application. For this reason, most cloud providers provide logging and monitoring services together with the compute service so that they can centralize all logging data and provide a comprehensive view of all events that are happening with the application at any moment. The user can leverage this service to obtain some monitoring capabilities out of the box when they deploy their application to the cloud environment. However, based on different applications and requirements, the user may expand these capabilities by adding custom logging logic or notification configurations to match their needs. Figure 13.6 shows a simple monitoring dashboard on Azure Cloud Service. Screenshot of simple monitoring dashboard on Azure Cloud Service. Figure 13.6. This picture provides an example of a simple monitoring dashboard on Azure Cloud Service. Used with permission from Microsoft Container Management Services in recent years, container management services, which encapsulate an application with the necessary operating system libraries for it to operate, have become one of the key innovations that have transformed the use of cloud infrastructures. In a nutshell, the container is a way to encapsulate an application with any operating systems library that is required for the application to operate. By using a container, the developer is not worried about the environmental mismatch between the environment where the application was developed and the environment where the application is run. This container can be run on top of any Linux kernel that provides support to the container runtime. Figure 13.7 shows how a container runs in a regular compute environment. It is also important to point out that the container technology is different from the virtualization technology used in virtual machines. Illustration of container with application code linked by downward arrow to system library, linked by downward arrow to operating system's kernel and hardware. These two are outside container. Figure 13.7. This diagram shows the high-level view of how a container runs in a regular compute environment. Attribution, copyright Rice University, OpenStax under CC by 4 license on the cloud environment. The container management service allows the user to deploy, operate, and scale any containerized application. It also includes several necessary components that help the user manage their containerized application better, such as the following: the container registry CR, or the registry where the user can version control each container image that they deployed into the cloud environment. The user can usually manage the container using image metadata such as namespace, image name, or image tags. The base container image, which is the foundational layer of a container provided by the cloud provider to build an application. The image is mostly up to date with secure patches and packages that allow the user to update their application with the latest security update. The Kubernetes environment, or Kubernetes K8s service, which is the most popular container orchestration system. This is a managed service that is usually provided by the cloud provider to allow the user to scale their containerized application in a Kubernetes environment. The K8s environment is one of the key systems to run a hybrid cloud environment where the user can run applications from both their local and cloud environment. Figure 13.8 shows a simple workflow to deploy a containerized application into Azure cloud environment. Architecting a hybrid cloud solution requires strong technical expertise in application development and containerized application, and it also requires deep knowledge of cloud solutions. The details on how to do it correctly will not be covered in this section. However, the hybrid solution should be the target for any user on their journey of migrating their application into the cloud. Arrow connected boxes, create Azure Container Registry ACR, create Azure Kubernetes Services AKS cluster and attach to ACR, build Docker images and publish to ACR registry, update Kubernetes K8 manifest, deploy application. Figure 13.8 on Azure, K8s can be part of a simple containerized application deployment workflow. Attribution, copyright Rice University, OpenStax under CC by 4 license, concepts in practice containers and virtual machines for deployment. Organizations can use containers or virtual machines. How do you decide which technology is more appropriate? Containers have more scalability and are practical if you're working with multiple environments and you want to package and run your applications in a manner that is predictable with repetition from one environment to the next. Virtual machines, VM, provide more environmental control and are practical if you need to use the same physical machine to install more than one operating system, as well as create more than one environment. Another consideration is the speed of software development. It is faster and easier to build and test new features on containers compared to VMs. However, VMs provide better security. While there's a lot to consider when deciding on containers versus VMs, both technologies offer important benefits, providing organizations with critical resources for deployment. Database management services today, database or any data management system is the heart of any application. However, managing a database is usually a difficult task as the data can be growing oversized both in size and in complexity. For this reason, most cloud providers provide several managed database services for any application that runs inside and outside of the cloud environment. There are 2 popular database management services: a relational database service RDS, in which the relationship between data is strictly managed. The data can be managed under a predefined data schema. This is the most common type of database that most developers are familiar with. Some popular examples of this type of database are Oracle DB, MySQL, or PostgreSQL. A NoSQL database in which the relationship between data is not strictly managed. The data can be managed under key value pair. This type of database has become popular in recent years with monitoring applications where the data needs to be written and captured quickly. Some popular examples of this type of database are MongoDB Atlas and Cassandra DB. The access pattern for these services is similar to how any application access to any managed database. Different secure authentication and authorization methods can be configured through the CLI or web console by the user, and the application can access the database from inside or outside of the cloud environment. Learning objectives: by the end of this section, you will be able to learn how to use Internet of Things Cloud PaaS services, learn how to use shallow and deep machine learning Cloud PaaS services, learn how to use blockchain Cloud PaaS services, understand PaaS services support for extended reality applications, understand PaaS services support for 3D 4D printing services, relate to PaaS services for cloud application development for businesses that look for all existing features in IaaS. As well as a service that provides a complete platform to develop, test, and launch their applications, Platform as a Service (PaaS) has become one of the top options, on top of servers. Network and security that IaaS provides, PaaS also includes middleware such as operating systems and development tools that enable quick application development and market launch. As the cloud provider manages more layers, PaaS will require less time and skill from the engineering team to manage their infrastructure. It will provide freedom for the company to focus on developing applications and providing services. However, because of those abstracted services, PaaS may have higher costs with dependency on the particular platform or vendor. The higher cost may come later when the organization explores different technical decisions and cloud vendors. In this section, we will explore various PaaS services that enable organizations to effectively launch and maintain large-scale applications. This includes AI incorporations or XR platforms that allow for operations of scripting and modeling. Through real-life examples, we can analyze how companies slash costs while also accelerating time to market and application development. Internet of Things services. A 5G network enables mobile computing at the edge of modern telecommunication networks with support for a variety of IoT devices, including laptops, smartphones, and smartwatches. 5G has higher radio frequencies, which transfer considerably more data over the air at faster speeds while reducing congestion and lowering latency. Thanks to 5G, more IoT devices can be used simultaneously within the same geographic area. As a result, today's dynamic information networks consist of interconnected sensors, actuators, mobile phones, robotics, and smart devices. IoT network traffic falls broadly into two categories: telemetry and telecommand. One category, telemetry, aggregates data generated by sensors and devices and sends them to a server. The other category, telecommand, sends commands across a network to control devices or sensors. Figure 13.9 illustrates the typical flow of IoT data generated by mobile edge devices and data processing and storage via cloud PaaS services. Illustrations showing back and forth between user, applications, operating system, device drivers, and devices. Figure 13.9 generally, this is how IoT data flow via mobile edge devices, data processing, and storage via cloud PaaS services. Attribution, copyright Rice University, OpenStax under CC by 4 license to serve the purpose of IoT. Several application layer protocols have been developed, such as Message Queuing Telemetry Transport, MQTT, Advanced Message Queuing Protocol, AMQP, Constrained Application Protocol, CoAP, Extensible Messaging and Presence Protocol, XMPP, and Simple Text-Orientated Messaging Protocol, STOMP. This was necessary because application layer protocols, such as HTTP, are not suitable for IoT telemetry and telecommand applications. HTTP is designed for one-to-one communication rather than one-to-many communication between many sensors and one server, and is a reliable protocol for web applications. However, HTTP supports unidirectional synchronous request-response communication and cannot send data in both directions simultaneously. IoT sensors cannot work efficiently in a synchronous manner. HTTP also is not designed for event-based communication. Generally, HTTP's scalability is achieved by loading the server, which puts a heavy load on sensor devices connected to multiple other devices. In addition, HTTP uses high power consumption, making it unsuitable for advanced wireless sensor networks. To understand how IoT application layer protocols work, consider MQTT, which is an example of a lightweight application layer messaging protocol. It is based on the publish-subscribe pub-sub model typically used for message queuing and telemetry applications. Multiple clients or sensors can connect to a central server known as a broker and subscribe to topics that interest them. Through the broker, which is a common interface router for sensor devices to connect to and exchange data, these clients also have the option of publishing messages regarding their topics of interest. To make the communication reliable, MQTT uses a TCP connection on the transport layer for connections between sensors and the broker. Big cloud vendors use IoT protocols such as MQTT to provide IoT PaaS services and related frameworks that facilitate the interactions of IoT devices with the cloud. The use of these services makes it possible to build and deploy innovative IoT solutions without developing and managing IoT frameworks on local computers. In particular, Microsoft Azure IoT manages cloud services that can interconnect, monitor, and control billions of IoT assets. An IoT solution is typically made up of one or more IoT devices that communicate with one or more back-end services hosted in the cloud. IoT devices can be constructed as circuit boards with sensors attached that use Wi-Fi too. Connect to the internet, e.g., presence sensors in a room. Devices may be prototyped using a Raspberry Pi or the Microsoft MX Chip IoT Dev Kit, which has built-in sensors for temperature, pressure, and humidity, as well as a gyroscope, accelerometer, and magnetometer. Microsoft also provides an open-source IoT device SDK to help build apps on devices. In addition, Microsoft's IoT Edge and IoT Hub frameworks can be used to facilitate the operation of IoT applications at the edge and the collection and transfer of data to the cloud via common communication protocols such as MQTT and AMQP. The technologies, PaaS services, and solutions provided by Azure IoT are summarized in Table 13.1. Oz, GCP, and IBM Cloud also provide equivalent IoT PaaS services and related capabilities. IoT Central Application Templates IoT Solutions Azure Services for IoT and Edge Device Support Retail Health Energy Government Azure IoT Central Managed Application Platform Azure IoT Hub Device Provisioning Service Azure Digital Twins Azure Time Series Insights Azure Maps Azure Sphere Azure IoT Device SDK Azure IoT Edge Azure Data Box Edge Reference Architecture and Accelerators PaaS Azure Stream Analytics Azure Cosmos DB Azure AI Azure Cognitive Services Azure ML Azure Logic Apps Windows IoT Azure Certified for IoT Device Catalog Azure Stream Analytics Azure Storage Dynamics Connected Field Service SaaS Azure Active Directory Azure Monitor Azure DevOps Power by Azure Data Share Azure Spatial Anchors Azure ML Azure SQL Azure Functions Azure Cognitive Services Table 13.1 IoT Technologies Services and solutions available through Microsoft Azure Shallow and Deep Machine Learning Services. IoT services provided by big cloud vendors include both shallow machine learning, which has few neuron layers, and deep machine learning, which has many neuron layers. PaaS services enable application developers to leverage machine learning capabilities on the cloud. Developers can build and deploy innovative machine learning solutions without using local computers to set up and manage machine learning frameworks, such as Apache Hadoop or Spark, along with related libraries and/or tools. This includes building and deploying solutions that require using and streaming data analytics. In addition to Microsoft, AWS, GCP, and IBM Cloud also provide shallow and deep PaaS services and related capabilities. Big Data Analytics Services. The process of analyzing big data to find correlations, consumer preferences, market trends, and related information is referred to as big data analytics. It is important to help organizations with decision-making processes. Big data analytics processes usually require training models using data sets with a manageable number of descriptive features. As such, big data analytics requires shallow rather than deep machine learning services. Tools for big data analytics include big data analytics frameworks, machine learning libraries, and analytics machine learning tools. Big data analytics frameworks various cloud vendors including Amazon, Cloudera, Dell, Oracle, IBM, and Microsoft offer an implementation of the Apache Hadoop or Spark stacks that are useful to support big data analytics projects. Other cloud data analytics frameworks include Amazon Elastic MapReduce, EMR, Amazon Athena, Azure HD Insight, Azure Data Lake, and Google Cloud Data Lab. EMR is a useful framework to host Spark. HD Insight is similar to EMR in power and it supports Spark, Hive, HBase, Storm, Kafka, and Hadoop MapReduce. HD Insight guarantees 99.9% availability and integrates various programming tools such as Visual Studio and supports various programming languages like Python, R, Java, and Scala, as well as net languages. As illustrated in the Azure Data Lake conceptual view, Figure 13.1, HD Insight includes all the usual Hadoop and Yarn components, such as Hadoop File System, HDFS, as well as tools that integrate other Microsoft Business Analytics tools such as Excel and SQL Server. Illustration of Azure Data Lake conceptual view, Data Lake Analytics, USQL and HD Insight Spark, Hadoop, Hive, Pig, Yarn, connected to HDFS, WebHDFS, Azure Data Lake Store, structured and unstructured big data. Figure 13.1, this graphic shows the big data analytics tools available in HD Insight with Azure Data Lake. Attribution, copyright Rice University, OpenStax under CC by 4 license. Big data machine learning libraries. Machine learning libraries have algorithms and functions in place to develop machine learning models needed for big data analytics. For example, Spark includes the MLib scalable machine learning library and the GraphX API for graphs and graph parallel computations. MLib offers classification, regression, clustering, and recommender system algorithms. MLib was originally built directly on top of the Spark RDD abstraction. It provides an API to specify data frames, transformers, estimators, and a high-level API for creating ML pipelines. GraphX is a Spark component that implements programming abstractions based on the RDD abstraction. GraphX comes with a set of fundamental operators and algorithms to work with graphs and simplify graph analytics tasks. mlib and GraphX are available to application developers via Azure ML and ML programming offerings from other cloud vendors. Big Data Analytics Machine Learning Tools Azure Machine Learning, ML, is a cloud portal for designing and training machine learning cloud services. Azure also provides Databricks, which is an Apache Spark-based analytics platform optimized for the Microsoft Azure cloud environment, as well as the MLNet open source and cross-platform machine learning framework. Amazon's AWS machine learning service, i.e. Amazon SageMaker, like Azure ML, can be used to create a predictive model based on the training data you provide. It requires much less understanding of ML concepts than Azure ML. Its dashboard presents a previous list of experiments, models, and data sources that enables developers to define data sources and ML models, create evaluations, and run batch predictions. As illustrated in Figure 13.11, it is based on a drag-and-drop component composition model. You build a solution to a machine learning problem by dragging solution parts from a palette of tools and connecting them into a workflow graph. You then train the solution with your data. When you are satisfied with the results, you ask Azure to convert your graph into a running web service using the model you trained. The tool supports customized machine learning as an on-demand service. Screenshot of Azure ML, a drag-and-drop component composition model, showing options for tools to create a workflow. Figure 13.11 Azure ML is based on a drag-and-drop component composition model that enables you to build a solution to a machine learning problem. Used with permission from Microsoft, this is another example of serverless computation. It does not require you to deploy and manage your VMs. The infrastructure is deployed as you need it, and if your web service needs to scale up because of demand, Azure scales the underlying resources automatically. Amazon also provides a portal-based tool, Amazon Machine Learning, that allows you to build and train a predictive model and deploy it as a service. In addition, both Azure and Amazon provide pre-trained models for image and text analysis in the Azure Cognitive Services and the Amazon ML platform, respectively. Think it through using avatars in virtual reality environments. Avatars are a popular way to represent ourselves graphically online. Can avatars in the metaverse's virtual reality environment make use of big cloud PaaS capabilities to operate semi-autonomously? If they're semi-autonomous, they'll be able to act independently with limited control from users. What ethical consequences could this pose? Streaming big data analytics services. Vendors provide various services to facilitate streaming big data analytics in the cloud, such as Spark Structured Streaming, Amazon Kinesis Data Firehose and Kinesis, Azure Stream Analytics, and Google Dataflow based on Apache Beam. Spark Structured Streaming also provides another high-level concept called the D-stream, which represents a continuous stream of data as a sequence of RDD fragments with windowed computations. Spark Structured Streaming leverages Spark Core and its fast scheduling engine to perform streaming analytics. Amazon Firehose, which is designed for extreme scale, can load data directly into Amazon S3 or other Amazon services. Kinesis Data Analytics for SQL applications provides SQL-based tools for real-time analysis of streaming data from Kinesis Data Streams or Firehose. Kinesis Data Streams provides ordered, replayable, real-time streaming data. Various open-source frameworks such as Kafka, Storm, Rising Wave, Apache Spark, Apache Flume, Apache Beam, and Apache Flink are also available to process streaming data on local machines. Table 13.2 compares Firehose to Kinesis Data Streams. The two primary components of the Azure Stream Analytics are the Azure Event Hub Service and Stream Analytics Engine. Feature Firehose Kinesis Data Streams Purpose Service for transferring data into third-party tools, streaming service provisioning fully managed, and has no administration managed, but requires shards configuration scaling automated scaling, based on demand manual scaling. Data storage not included offers data storage that can be configured from 1 to 365 days. Replay capability no. Replay capability is not supported. Yes. Replay capability is supported. Message propagation almost real-time, depending on buffer size or time. Real-time. Table 13.2 Firehose versus Kinesis Data Streams. Apache Beam is the open-source release of the Google Cloud Dataflow system. Beam treats the batch and streaming cases uniformly and supports pipelines to encapsulate computations, as well as peak elections, which represent data as they move through a pipeline. Beam enables computational transformations that operate on peak elections, produces peak elections, and relies on sources and sinks from which data are read and to which data are written, respectively. Deep learning and generative AI services. All the big clouds today provide integrated machine learning services that use various techniques to create models that leverage prior experience and make it possible to improve the ability of machines to perform tasks. These services may be used as part of big data analytics and streaming big data analytics techniques, as explained in the previous subsections. Deep learning (DL) is another technique that leverages artificial neural networks, e.g., RNNs, CNNs, GANs, to create models that perform predictive tasks requiring special training and the ability to relate to a vast combination of labels patterns, e.g., image recognition, speech recognition, language translation. There are various types of deep learning improvements that include reinforcement learning and transfer learning, among others. Artificial intelligence, AI, is also a technique that leverages ML to enable computers to mimic human intelligence. Generative AI (Gen AI) is a subset of AI that uses techniques such as deep learning and transformers to generate new content, e.g., create images, text, or audio that matches a request. Transformers are special types of ML model architectures that are suited for solving problems that contain sequences such as text or time series data. Transformers have been used recently to solve natural language processing problems, e.g., translation, text generation, question answering, text summarization, and various transformer implementations have been quite successful, including the bidirectional encoder representations from transformers BERT and the generative pre-trained transformers GPTs. ML models that support Gen AI are referred to as large language models (LLMs) and are foundation models (FMs). LLMs are typically tuned towards specific conversational applications and require more parameters and data-intensive training. Foundation models (FMs) are more general purpose than LLMs and less data-intensive. Examples of LLMs include OpenAI's ChatGPT, Google Gemini, Meta M2M100 and Llama, IBM's Granite model, Anthropic's Claude models, Mistral AI's models, and many others. LLMs and FMs can be augmented using retrieval augmented generation (RAG) AI frameworks that supplement the FM's internal representation of information to improve the quality of the LLM-generated responses. Cloud vendors provide DL services in the form of programming frameworks that help implement deep learning applications using differentiable programming. Gen AI services provided by the big clouds and other vendors are prompt interfaces that are specially engineered to allow users to get the most out of an LLM by including a sufficient amount of information in the prompts they create. The following provides a non-exhaustive list of DL services provided by some of the big clouds: Amazon AWS Deep Learning Services, Amazon Deep Learning AMIs, DLAMIs. Amazon DLAMIs are customized machine images that may be used for deep learning in the cloud. They can be deployed on various types of Amazon VMs, i.e., EC2 instances, including CPU-only instances or the latest high-powered multi-GPU instances. DLAMIs come pre-configured with NVIDIA CUDA and NVIDIA cuDNN and the latest releases of the most popular deep learning frameworks. Amazon released the Amazon Deep Learning AMI with Conda, which uses Conda virtual environments to isolate each framework, allowing you to switch between them at will without their dependencies conflicting. The full list of supported frameworks by Amazon Deep Learning AMI with Conda includes PyTorch, TensorFlow 2, and Apache MXNet, now retired but can still be accessed and used. Starting with the V18 release, Amazon Deep Learning AMI with Conda no longer includes the CNTK, CAF, CAF2, Theno, Chainer, or Kira's Conda environments. Configuring the Amazon DLAMIs to use Jupyter is easy. Go to the Amazon Marketplace on the EC2 portal and search for Deep Learning. You will find the DLAMIs, then select the server type you would like to use. If you simply want to experiment, it works well with a no GPU option. When the VM comes up, log in with SSH and configure Jupyter for remote access. Amazon Lex. Amazon Lex is an IA chatbot that allows users to incorporate voice input and conversational interfaces into applications. It is an extension of Amazon's Echo product, a networked device with a speaker and microphone that you can ask questions through the Alexa service, e.g., questions about the weather, event scheduling, news, and music. It is possible to associate Echo voice commands with the launching of an Amazon Lambda function that executes a cloud application. Amazon Polly. Amazon Polly is the opposite of Lex. It turns text into speech for dozens of languages with a variety of voices and uses the Speech Synthesis Markup Language, SSML, to control pronunciation and intonation. Amazon Recognition. Amazon Recognition is at the cutting edge of deep learning applications. It takes an image as input and returns a textual description of the items that it sees in that image. This includes objects, landmarks, dominant colors, activities, and faces. It also performs detailed facial analysis and comparisons and can identify inappropriate content that appears in images. Microsoft Azure Deep Learning Services, Azure Data Science VMs, DSVMs. Azure DSVMs are Azure Virtual Machine Images, pre-installed, configured, and tested with several popular tools that are commonly used for data analytics, machine learning, and AI development and training. Azure Machine Learning (ML). Azure ML is a cloud service that is designed to help accelerate and manage machine learning project lifecycles. It can be used to train and deploy ML models and manage machine learning operations via ML Ops. You can create a model in Microsoft ML or use a model built from an open-source platform such as PyTorch, TensorFlow, or scikit-learn. ML Ops tools help you monitor, retrain, and redeploy models. As noted earlier, Azure also provides the MLNet machine learning framework. Azure AI Services. Azure AI Services are APIs SDKs that can be used to build applications that support natural methods of communication, i.e., see, hear, speak, understand, and interpret user needs. These services include support for vision, e.g., object detection, face recognition, optical character recognition, speech, e.g., speech-to-text, text-to-speech, speaker recognition, languages, e.g., translation, sentiment analysis, key phrase extraction, language understanding, and decision, e.g., anomaly detection, content moderation, reinforcement learning. Google Deep Learning Services, Deep Learning VMs. Deep Learning VM images are virtual machine images optimized for data science and machine learning tasks. All images include pre-installed ML frameworks and tools and can be used on VM instances with GPUs to accelerate data processing. Tasks ML frameworks supported include TensorFlow and PyTorch. Google Machine Learning APIs. Google provides various APIs to services that can be used to build applications that support natural methods of communication, including Cloud Vision to understand the content of an image, Cloud Speech to Text to transcribe audio to text, Cloud Translation to translate an arbitrary string to any supported language, and Cloud Natural Language to extract information from text. The following provides more information related to GenAI services provided by the big clouds. AWS GenAI Services. Amazon AWS provides various GenAI tools, including the Amazon Q AI-powered assistants and the Amazon Bedrock suite of LLMs, FMs, and generative AI tools. Amazon SageMaker may be used to build, train, and deploy FM models at scale. Microsoft Azure GenAI Services. The Azure OpenAI Service and the Azure AI Studio can be used to create custom Copilot and generative AI applications. Microsoft has partnered with OpenAI, the company that is developing ChatGPT. It also provides the Phi family of small language models, SLMs, that are low-cost and low-latency alternatives to LLMs in some cases. Google GCP GenAI Services. Vertex AI, Generative AI Studio, and Vertex AI Model Garden are various solutions that Google provides to support the creation of generative AI applications. Google also provides the Gemini family of generative AI models that are capable of processing information from multiple modalities, including images, videos, and text. IBM Cloud GenAI Services. IBM Watsonx. AI Studio brings together generative AI capabilities that are powered by FMs and ML. It provides tools to tune and guide models based on enterprise data as well as build and refine prompts. IBM also develops custom Granite AI foundation models that are cost-efficient and enterprise-grade. Other Gen AI services. In addition to the Gen AI services and tools mentioned here, many other vendors focus on the creation of LLMs, SLMs, and FMs. Here are a few of them: OpenAI's ChatGPT, Meta Llama, Anthropic Claude, Mistral AI ML toolkits. Performance ML toolkits can be used for various tasks, such as scaling a computation to solve bigger problems. One approach is the SBMD model of communicating sequential processes by using the Message Passing Interface (MPI) standard model. Another is the Graph Execution Dataflow model used in Spark, Flink, and the deep learning toolkits. You can write ML algorithms using either MPI or Spark. You should be aware that MPI implementations of standard ML algorithms typically perform better than the versions in Spark and Flink. Often, the differences are factors of orders of magnitude in execution time, but the MPI versions are harder to program than the Spark versions. Blockchain services. Blockchains use a distributed ledger system to store data and transactions in an open-source database that enables you to build applications that allow multiple parties to securely and transparently run transactions and share data without using a trusted central authority. With Blockchain 2, developers have a mechanism that allows programmable transactions, which are modified by a condition or set of conditions. Blockchain 2 is not limited to supporting transactions. It can also handle microtransactions, decentralized exchange, and creating and transferring digital assets. Blockchain 2 also has the ability to handle smart contracts, which are scripts executed in a Blockchain 2 environment. the codes of smart contracts are accessible to the public and anyone can verify the correctness of code execution. The actual verification is carried out by miners in the blockchain environment, and this ensures honest execution of the contract. Smart contracts rely on cryptography to secure them against tampering and unauthorized revisions. A blockchain network is a peer-to-peer network that allows people and organizations who may not know one another to trust and independently verify the records of financial and other transactions. This improves the efficiency and immutability of transactions for business processes such as international payments, supply chain management, land registration, crowdfunding, governance, financial transactions, and more. Ethereum.org implements a blockchain 2 decentralized computing platform for Web3 and provides a language to write transaction scripts. Web3 applications are referred to as dApps and may be deployed on blockchain 2 decentralized computing platforms. Ethereum.org provides its own development environment, i.e., remix and programming languages such as Solidity to develop and deploy contracts. Public test networks such as Goerli may be used to develop and test contracts before deploying them on the Ethereum platform. Web3 APIs are available for various programming languages such as JavaScript, Python, Haskell, Java, Scala, and PureScript to facilitate the creation of applications that interact directly with the Blockchain 2 platform. Using PaaS blockchain services on AWS, Oracle, GCP, and IBM Big Clouds, it is possible to create a blockchain decentralized computing platform to facilitate the deployment of Web3 dApps. Big Clouds provide clusters of VMs that may be leveraged as P2P nodes within a blockchain 2 decentralized platform implementation, such as Hyperledger. While Microsoft Azure offered PaaS services to create blockchain platforms, it has retired these services and partnered with ConsenSys and other companies to provide that support. Azure does provide products and services, Web3 developer tools, and security capabilities to help create Web3 applications and deploy them on partner platforms. Link to learn more about blockchain PaaS services available in the Big Cloud. You can visit multiple websites and explore blockchain features. For example, you can find information about AWS blockchain online. AWS Blockchain Services. AWS provides blockchain templates that help you create and deploy blockchain networks on Oz using different blockchain frameworks. AWS Managed Blockchain, which is shown in Figure 13.12, is used to configure and launch AWS CloudFormation stacks to create blockchain networks. The AWS resources and services used depend on the Oz blockchain template selected and the options to specify the fundamental components of a blockchain network.
Oz Blockchain Template, AWS CloudFormation. ECS Container Platform contains Elastic Load Balancing, Amazon S3, Multinode Blockchain Network, Blockchain Explorer and Monitoring, Amazon ECS, Amazon EC2, and ECR Registry, Blockchain Framework Containers. Figure 13.12. This graphic shows Oz blockchain templates, which are used to configure and launch AWS CloudFormation stacks to create blockchain networks. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Amazon Managed Blockchain is a fully managed service for creating and managing blockchain networks that supports the Hyperledger Fabric open source framework. You can use Managed Blockchain to create a scalable blockchain network quickly and efficiently using the AWS Management Console, the AWS CLI, or the Managed Blockchain SDK. Managed Blockchain scales to meet the demands of thousands of applications running millions of transactions. Once the blockchain network is functional, Managed Blockchain simplifies network management tasks by managing certificates, making it easy to create proposals for a vote among network members, and tracking operational metrics such as computing resources, memory, and storage resources. Figure 13 shows the basic components of a Hyperledger Fabric blockchain running on Oz. A network includes one or more members with unique identities. For example, a member might be an organization in a consortium of banks. Each member runs one or more blockchain peer nodes to run chain code, endorse transactions, and store a local copy of the ledger. Amazon Managed Blockchain creates and manages these components for each member in a network, and also creates components shared by all members in a network, such as the Hyperledger Fabric ordering service and the general networking configuration. Hyperledger Fabric ordering service blockchain connected to member Fabric peer node, then to AWS private link, then through VPC to Oz client. Figure 13. 13. This graphic shows the basic components of a Hyperledger Fabric blockchain running on Oz via a managed blockchain network. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. When creating a managed blockchain network, the creator chooses the blockchain framework and the addition of Amazon managed blockchain to use, and this determines the capacity and capabilities of the network as a whole. The creator also must create the first managed blockchain network member. Additional members are added through a proposal and voting process. There is no charge for the network itself, but each member pays an hourly rate, billed per second, for their network membership. Charges vary depending on the addition of the network. Each member also pays for peer nodes, peer node storage, and the amount of data that the member writes to the network. The blockchain network remains active as long as there are members. The network is deleted only when the last member deletes itself from the network. No member or Oz account, even the creator's Oz account, can delete the network until they are the last member and delete themselves. IBM Blockchain Services. IBM Blockchain Platform, IBP, is an IBM cloud offering that is built on Fabric, a blockchain infrastructure provided by the open-source Hyperledger project. IBP provides an integrated developer experience with smart contracts that can be easily coded in Node, Golang, or Java. You can use the new IBM Blockchain V's code extension to write client applications, based on the IBP console's integration of the Fabric SDK. IBP offers the possibility of deploying only the necessary components to connect to multiple channels and networks, while you maintain control of identities in your environment. Flexible and scalable, IBP can be run in any environment that IBM Cloud Private (ICP) supports, including Linux One. IBP simplifies the development and management of a blockchain network. It lets you accomplish the following tasks with just a few clicks in the easy-to-use interface. Automated deployment of Fabric, creation of custom governance policies, initial development, deployment of the application into production, including the creation of channels and deployment of chain code, inviting new members into the network, and managing identity credentials over time. Linux One is engineered for high performance, large-scale data, and cloud services. A single Linux One platform consolidates hundreds of x86 cores. The platform's dedicated I/O processors allow you to move massive amounts of data while maintaining data integrity. The option to have dedicated cryptographic processors that supplement the standard CPUs means encryption for data at rest and for data in transit. Partitions within IBM's Secure Service Container (SSC) technology help to protect data and applications from internal and external threats. The IBM blockchain solution leverages Kubernetes K8s, which is an open-source system for the automation of deployment, scaling, and management of containerized applications. The Kubernetes framework runs distributed systems resiliently and takes care of scaling requirements, failover, deployment patterns, and so forth. Kubernetes restarts containers that fail, replaces containers, kills containers that do not respond to your user-defined health check, and does not advertise them to be used until they are ready to serve. The key aspects of Kubernetes include the following: service discovery and load balancing, storage orchestration, automated rollouts and rollbacks, automatic bin packing, self-healing, secret configuration management. Other components of the IBM blockchain solution include IBM Cloud Private (ICP), Gluster FS, MIBM Secure Service Container, and the IBM Blockchain Platform. ICP is a private cloud platform for enterprises to develop and run workloads locally. It consists of PaaS and developer services that are needed to create, run, and manage cloud applications. Gluster FS is a scalable network file system suitable for data-intensive tasks such as cloud storage and media streaming. It aggregates various storage servers into one large parallel network file system. IBM Secure Service Container (SSC) provides the base infrastructure on Linux One for container-based applications, either for hybrid or private cloud environments. This secure computing environment delivers tamper-resistant installation and runtime operations. Oracle Blockchain Services. Oracle also provides a blockchain platform, as illustrated in Figure 13. 14. Oracle's blockchain components include a network of validating nodes, i.e., peers, a distributed ledger, i.e., linked blocks, world state, and history database, an ordering service for creating blocks, and membership services for managing organizations in a permissioned blockchain. Illustration of blockchain platform including membership service, world state, order, peers, smart contracts, vendors, POS, invoicing, shipping, payments, applications, and supply chains and accounts payable at organizations. Figure 13. 14. As this diagram shows, Oracle's blockchain components include a network of validating nodes, a distributed ledger, an ordering service for creating blocks, and membership services for managing organizations in a permitted blockchain. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. The smart contracts, chain code, layer consists of chain code programs that contain the business logic for updating the ledger, querying data, and/or publishing events. Chain codes can read the ledger data to verify conditions as part of any proposed updates or deletes and trigger custom events. Updates and deletes are proposed or simulated and are not final until transactions are committed following consensus and validation protocols. New or existing applications can register enroll organizations as members, submit transactions, invoke smart contracts, to update or query data, and consume events emitted by the chain codes or by the blockchain platform. The Oracle blockchain platform is based on the Hyperledger Fabric project from the Linux Foundation, and it extends the open-source version of Hyperledger Fabric. Preassembled PA-S, Oracle's blockchain platform, includes all the dependencies required to support a blockchain network such as compute, storage, containers, identity services, event services, and management services. The Oracle blockchain platform includes the Blockchain Network Console to support integrated operations. GCP Blockchain Services. Google offers Blockchain Node Engine, a fully managed node hosting service for Web3 development that minimizes the need for node operations. Web3 companies that require dedicated nodes can relay transactions, deploy smart contracts, and read or write blockchain data. Blockchain Node Engine supports Ethereum, enabling developers to provision fully managed Ethereum nodes with secure blockchain access. With blockchain, Google's focus is on cryptocurrency and blockchain analytics tools that provide deep blockchain transaction history data sets and deeper sets of queries that enable multi-chain meta-analysis and integration with conventional financial record processing systems. Google is particularly interested in providing transaction history for cryptocurrencies that have similar implementations, such as Bitcoin, Ethereum, Bitcoin Cash, Dash, Dogecoin, Ethereum Classic, Litecoin, and Zcash. Google also offers machine learning tools that may be used to search for patterns in transaction flows and provide basic information on how a crypto address is used. Extended reality services. When discussing extended reality services, there are generally two types: virtual reality (VR), which enables a computer-generated, interactive, 3D environment in which a user is immersed, and augmented reality (AR), which supplements the real world with virtual, computer-generated objects that appear to coexist in the same space as the real world. The key distinction between VR and AR is that VR is meant to immerse the user in a virtual environment, while AR introduces virtual elements to the real world. A VR system typically uses a headset in combination with a variety of sensors to track the user's movement and relay the appropriate images and feedback, creating the sensation of interacting with the virtual world. An AR system typically relies on clear lenses or a pass-through camera that allows users to see the world around them in real time, while virtual elements are projected on the lenses or rendered on the camera output. There is also extended reality (XR), a reality service that involves both real and virtual environments. Microsoft introduced the term mixed reality (MR), which is a form of XR. XR encompasses both virtual and real environments and often integrates cloud services like IoT, ML, and blockchain. Three components are needed to make an XR system functional: a head-mounted display, a tracking system to recognize and follow physical objects, and mobile computing power. Today, XR is enabled via the use of headsets and haptic gloves, which are IoT devices. Instead of accessing applications with traditional computers, XR makes it possible to access applications through head-mounted hardware or gloves that interact directly with human senses, such as vision, hearing, and touch. In addition, ML may be needed within a mixed reality environment to do things such as generate prediction and perform recognition in a way similar to what we use ML for in the real world. In some sense, XR is the base technology for WebX. Zero, i.e., the real metaverse, not Meta's metaverse. Many XR commercial headsets are available for use, including Microsoft HoloLens, Google Cardboard, and Meta Quest. Creating virtual reality scenes for VR or virtual objects or avatars that can be viewed via XR headsets requires the use of a 3D engine tool such as Unity or Unreal Engine. Unity is a widely used cross-platform 3D engine and integrated development environment, IDE. Its uses include developing 3D content and games for different platforms, such as PCs, consoles, mobile devices, AR/VR target devices, and the web. Unity is a complex system with a steep learning curve. Successful deployment of applications also requires development frameworks and plugins, such as Microsoft Mixed Reality Toolkit, MRTK, or OpenXR. OpenXR can be accessed by 3D engines, e.g., Unity, Unreal, the WebXR device API, as well as XR applications running on base stations to facilitate deployment to or integration with various devices, including 3D head-mounted displays, e.g., Microsoft HoloLens, Apple Vision Pro, MetaQuest, trackers, e.g., body, hand, object, eye, haptic devices, and cloud 5G infrastructure. XR applications provide controlled and repeatable scenarios, rehearsing muscle memory and situational awareness. VR applications make it possible to explore places otherwise inaccessible, and also have the potential to provide access to resources that may be prohibitively expensive or otherwise inaccessible. VR and AR applications provide innovative ways to visualize and manipulate data. Azure MiSTer services and related PaaS services. Microsoft and the Azure Cloud provide various services for its Kinect and HoloLens products. This includes the Azure Kinect Sensor SDK, a developer kit with advanced AI sensors for building computer vision and speech models. Azure Kinect is a cutting-edge spatial computing developer kit with sophisticated computer vision and speech models, advanced AI sensors, and a range of powerful SDKs that can be connected to Azure Cognitive Services. Microsoft also offers HoloLens 2, which is a set of smart glasses, and the HoloLens emulator, both of which allow users to test holographic applications on a PC without a physical HoloLens 2 or HoloLens 1, including the HoloLens Development Toolset. Using the HoloLens emulator requires learning keyboard and mouse commands to facilitate walking in a given direction, looking in different directions, and making controlling gestures and hand movements. The emulator uses a Hyper-V virtual machine, which means human and environmental inputs being read by HoloLens sensors are simulated from a keyboard, mouse, or Xbox controller. Users do not need to modify projects to run on the emulator because the apps do not recognize that they are not running on a real HoloLens. Users can join the HoloLens Developer Program and learn to develop and deploy their own 3D models. Alternative development environments for HoloLens include Unreal Engine and BuildWagon. BuildWagon provides an online code editor that allows users to write code in JavaScript and view the results on the same screen or directly on the HoloLens. A HoloLens device is not required, and code is hosted on the cloud to allow multiple developers to collaborate on the same project from different locations. BuildWagon's HoloBuild library provides ready-made components to expedite creation processes and access HoloLens special features. The Microsoft Mixed Reality Toolkit, MRTK, is a Microsoft-driven project that provides a set of components and features used to accelerate cross-platform MiSTer app development in Unity. It provides the cross-platform input system and building blocks for spatial interactions and UI, enabling rapid prototyping via an editor simulation that enables users to see changes immediately. It operates as an extensible framework that provides developers with the ability to swap out core components while supporting a wide range of platforms. Microsoft provides a detailed set of guidelines to assist with the development of mixed reality applications, covering application ideation, design, development, and distribution. Concepts in practice: innovation and big cloud PaaS. Innovation is a great concept, and the use of big cloud PaaS services enables it. Before big cloud PaaS services became available, it was difficult for companies to put in place the services and related infrastructure needed to develop innovative solutions. All of the PaaS services that are covered in this chapter require frameworks and resources, which are provided by the big clouds. Therefore, it is possible for companies to focus on applying these services to develop innovative solutions. As an example, you can simply go to Azure portal.com and type Data Science Virtual Machine in the search bar. You will then be provided with a choice of Linux or Windows VMs that come fully packed with all the framework and related APIs needed to implement the service. Microsoft Azure provides IoT Edge and IoT Hub frameworks that can be used to collect data from sensors located at the edge, e.g., weather sensors that measures temperature and humidity, and propagate the corresponding data to the Azure cloud so it can be analyzed to generate weather predictions. Therefore, big cloud PaaS services can be used today to enable and accelerate innovation. Also available on the Azure cloud are a number of PaaS services, including the following. Azure Storage Services may be used to store 3D models. Azure Remote Rendering, ARR, is a service that lets you render highly complex 3D models in real time and stream them to a device. ARR is generally available and can be added to your Unity or native C++ projects targeting HoloLens 2 or Windows desktop PC. Azure Object Anchors, AOA, is a mixed reality service that helps you create rich, immersive experiences by automatically aligning 3D content with physical objects. It makes it possible to gain a contextual understanding of objects without the need for markers or manual alignment. It also saves significant touch labor, reduces alignment errors, and improves user experiences by building mixed reality applications with object anchors. Azure Spatial Anchors, ASA, is a cross-platform service that allows you to build spatially aware mixed reality applications. With ASAs, you can map, persist, and share holographic content across multiple devices at a real-world scale. In particular, ASAs are used to create free-world anchors that persist across multiple application sessions. Azure Speech Service is a speech resource that may be used to recognize speech, synthesize speech, get real-time translations, transcribe conversations, or integrate speech into your bot experience. Azure AI Vision is a cloud-based computer vision API that provides developers with access to advanced algorithms for processing images and returning information. When a user uploads an image or specifies an image URL, Microsoft computer vision algorithms can analyze visual content in different ways based on inputs and user choices. GCP XR and related PaaS services. Google provides various XR and related PaaS services, including both Google AR and VR. The AR services include Google Lens, which can recognize things in images. AR in Google Search lets you bring 3D objects and animals into the world you see. Live View in Google Maps changes how the world looks to add directions and other information. AR stickers let you drop objects into photos taken with a Google Pixel camera. Google makes it possible for developers to develop AR applications using its Arcore geospatial API. Google also provides VR capabilities, including Cardboard, which is a cardboard VR headset that uses a phone as a virtual world generator unit. Deep Dream is a computer vision program that uses a convolutional neural network to find and enhance patterns in images to create dreamlike appearances. Google also makes it possible for developers to develop their own VR applications. Other XR and related PaaS services. Google isn't the only provider of XR and related PaaS services. For example, MetaQuest offers all-in-one VR headsets that developers can use to create a range of VR experiences, including mixed reality, designed for both work and play. In another example, With the Amazon Sumerian platform, Amazon develops XR tools and uses XR technology to support its retail businesses. For example, Amazon Sumerian makes it possible to create and run VR, AR, and 3D applications quickly and easily without requiring any specialized programming or 3D graphics expertise. It runs on popular hardware such as Meta Quest and Google Cardboard, as well as on Android and iOS mobile devices. Amazon Sumerian makes it possible to create virtual classrooms that let you train new employees around the world or enable people to tour a building remotely. The NVIDIA Omniverse platform is an easily extensible platform for 3D design collaboration and scalable multi-GPU, real-time, true-to-reality simulation. Omniverse revolutionizes the way individuals create, develop, and work together as teams, bringing more creative possibilities and efficiency to 3D creators, developers, and enterprises. YouTube also offers a VR experience through videos recorded with 360 or 3D cameras. Through YouTube VR, users can experience things such as skydiving, snowmobiling, and a hot air balloon ride. To ensure it is VR, look for the compass icon in the upper left of a video. 3D 4D printing services. The process of 3D printing, formerly known as additive manufacturing, is a process of designing static objects in 3 dimensions through additive processes in which successive layers of material are laid down under computer control. It is being used in applications such as medical prosthetics, aerospace components, and defense equipment. A 3D modeling program, such as AutoCAD, is used for designing the objects. Various cloud vendors are making 3D printing technology available on the cloud today, such as CraftCloud, which allows users to essentially create an order for a custom 3D printed part without having to actually own a 3D printer. Users can upload their 3D models to the CraftCloud platform, select their specifications, and receive their custom 3D printed part in the mail. The process of 4D printing, also supported as a platform as a service (PaaS) on some clouds, provides the capability of programming the fundamental materials used in 3D printing by creating objects that can change their form or function after fabrication. It is scalable and can use cloud-based environments that streamline the development and deployment of smart materials and dynamic structures. These services offer advanced computational resources and specialized software tools needed for designing, simulating, and controlling 4D printing processes, enhancing efficiency and innovation in creating adaptable and self-transforming products. 4D printing adds the elements of time and interactivity to 3D printing. 4D printing creates objects with dynamics and performance capabilities, so they are able to change their form or function after fabrication. These objects can be assembled, disassembled, and then reassembled to form macro-scale objects of desired shape and multifunctionality. This technology is based on 3 key capabilities: the machine, the material, and the geometric program. As an example, using this technology, the Stratasys Material Research Group developed a new polymer that could be expanded 150% when submerged in water. Industry Spotlight: 3D and 4D printing in healthcare. In healthcare, 3D and 4D printing has revolutionized imaging technology, improving processes such as mammography, radiation therapy, bronchoscopy, and ultrasounds. With benefits such as 3-dimensional imaging, better delivery processes for drugs, tissue engineering, and more sophisticated medical devices. 3D and 4D technology improves the quality of images and enables health professionals to provide more accurate diagnoses and better targeted treatments, improving patient care and often leading to better outcomes. Provide a specific example of how you think 3D and 4D printing are likely to improve healthcare in the next 5 years. Applications Development Services. Various application development support capabilities are provided as PaaS services on the big clouds. These services help organizations improve operations and include integration management, identity and security management, application lifecycle management, monitoring, and management and governance. Integration Management. Integration Management is a PaaS service that supports project management with tools for communication, project coordination, efficiency, and even conflict resolution. AWS, GCP, and IBM Cloud also provide integration management (PaaS) services and related capabilities. Identity and security management. With identity and security management supported by PaaS, organizations can help ensure that only authorized users have access to their systems and applications. AWS, GCP, and IBM Cloud also provide identity and security management (PaaS) services and related capabilities. Application Lifecycle Management. Application Lifecycle Management is a tool that guides the software application process from planning until the software is decommissioned and retired. Various application lifecycle management capabilities, including DevOps and migration, are provided as PaaS services on the big clouds. DevOps combines people, processes, and products to enable continuous delivery of value to end users. DevOps enables you to build, test, and deploy any application, either to the cloud or on-premise. AWS, GCP, and IBM Cloud also provide DevOps PaaS services and related capabilities. Migration services minimize the time and resources required to migrate an on-premises environment to the cloud. AWS, GCP, and IBM Cloud also migration services and related capabilities. Monitoring. Typical monitoring services include application log analytics to drive resource autoscaling. Monitoring ensures that organizations realize when they have application issues that need immediate attention and areas where applications can perform better. Monitoring also provides data about applications that are underutilized and overloaded. AWS, GCP, and IBM Cloud also provide monitoring PaaS services and related capabilities. Management and governance. Generally, management and governance capabilities include recovery, cost management and billing, and other services. AWS, GCP, and IBM Cloud also provide management and governance PaaS services and related capabilities. Identity and security management. With identity and security management supported by PaaS, organizations can help ensure that only authorized users have access to their systems and applications. AWS, GCP, and IBM Cloud also provide identity and security management (PaaS) services and related capabilities. Application Lifecycle Management. Application Lifecycle Management is a tool that guides the software application process from planning until the software is decommissioned and retired. Various application lifecycle management capabilities, including DevOps and migration, are provided as PaaS services on the big clouds. DevOps combines people, processes, and products to enable continuous delivery of value to end users. DevOps enables you to build, test, and deploy any application, either to the cloud or on-premise. AWS, GCP, and IBM Cloud also provide DevOps PaaS services and related capabilities. Migration services minimize the time and resources required to migrate an on-premises environment to the cloud. AWS, GCP, and IBM Cloud also migration services and related capabilities. Monitoring. Typical monitoring services include application log analytics to drive resource autoscaling. Monitoring ensures that organizations realize when they have application issues that need immediate attention and areas where applications can perform better. Monitoring also provides data about applications that are underutilized and overloaded. AWS, GCP, and IBM Cloud also provide monitoring PaaS services and related capabilities. Management and governance. Generally, management and governance capabilities include recovery, cost management and billing, and other services. AWS, GCP, and IBM Cloud also provide management and governance PaaS services and related capabilities. Learning objectives. By the end of this section, you will be able to analyze specific applications of AI through XR technology, understand the impact of the development of super society capabilities, including nanotechnology, robotics, and supercomputers, discuss the advantages and challenges faced by the development of IaaS and supersystems. Recent advances with superintelligent AI allow for the seamless vision of incorporating networked autonomous systems into reality. These systems, known as Intelligent Autonomous Networked Supersystems, IaaS, are becoming the next major development for chained computing, where intelligent chains of autonomous machines work together as a system to make decisions and take action. IANS are highly interconnected AIs, forming complex networks that collaborate while utilizing quick and extended exchange of data to promote growth. In this section, we will analyze current applications of IANS and supersystems that are implemented and traffic large-scale systems and businesses with their applications. By going through real-life examples, we can evaluate the potential and critically examine the current challenges and limitations in the development and deployment of extensive IANS and similar supersystems that use intelligence to improve industries such as healthcare. Web platforms and smart ecosystems applications. Today's web incorporates hybrid multiclouds that continuously evolve. As shown in Figure 1315, these hybrid multiclouds power myriad innovative technology components that make it possible to create innovative solutions as the web continues to evolve. Illustration of web evolution. Prior to 1980s discussion and newsgroup service, 1980s email, chat, news, bulletin, early 1990s www goes mainstream, text-based websites, late 1990s e-commerce, website design, animation, interactivity, current Web 2.0, social media, mobile internet. Figure 13. 15. As this diagram shows, the web has evolved and experienced many breakthroughs and disruptions. Credit, Modification of History of Online Service by Viviense/Wikimedia Commons. CC0, in particular, recent advances in mobility and networking, such as 5G, have made it possible to minimize the latency of traditional web and mobile applications. This has led to a proliferation of social networks that enable efficient access to various types of content and global instant communication and collaboration. In addition, virtualization technology has made it possible to create powerful cloud platforms that facilitate access to infrastructure and platform services, as described earlier in this chapter. This progress is leading to global acceptance of the next-generation hybrid Web 3.0, which makes it possible to combine traditional Web 2.0 applications with Blockchain 2.0 capabilities. Blockchain is characterized by real-time transactions, scalability, and unlimited decentralized storage. Further improvements are on the horizon to provide a more scalable, fast, unlimited, and completely secure blockchain infrastructure via Blockchain 3.0.40. To build on this, Web 4.0 and 5.0 are already on the way as the metaverse is being positioned as the successor to today's internet. Metaverse is a concept that originated in the 1992 novel Snow Crash, in which people used the metaverse as an escape from a dystopian world, an idea also later explored in the novel and film Ready Player One. Metaverse embodies a unified, immersive digital world that is tightly connected to the physical world. In the metaverse, people can interact without physical or geographic constraints and enjoy a compelling sense of social presence. The metaverse is characterized by two key features. It is persistent, with its collective network of 3D rendered virtual elements and spaces available throughout the world 24/7. It is also shared, giving a vast number of users simultaneous access and the ability to use the metaverse to interact. The metaverse functions with 6 key layers that include infrastructure, e.g., chips and processors, cloud infrastructure, access interface, e.g., haptics, headsets, smart glasses, virtualization tools, e.g., 3D design engines, avatar development, virtual worlds, centralized and decentralized, economic infrastructure, e.g., payments, crypto wallets, and non-fungible token, NFT marketplaces using NFTs with a digital signature that cannot be exchanged or equated to another item, and experiences, e.g., gaming, virtual real estate concerts. Industry applications. As of 2024, the online worlds promoted by metaverse proponents are not fully formed and functional just yet, but platforms and games like Second Life, Roblox, and Decentraland are indicators of the future once the metaverse is fully operational. The metaverse is expected to rely on technologies such as virtual reality headsets, advanced haptic feedback, and 3D modeling tools to power immersive digital environments. To understand the potential of the metaverse and mixed reality technology, let's consider their applications in the areas of education and healthcare. Enhanced learning experiences, mixed reality, can provide visuals and relatable examples to help students perceive theoretical information in complex topics such as biology, anatomy, physics, and math. Medical students can learn anatomy and practice examining the body with XR apps that represent the human body inside and out. Chemistry students can conduct experiments using different chemical combinations and see results with no harm to students and school property. Nursing students can use simulations to learn and prepare for unique situations that they'll encounter in clinical settings. Students can also take field trips to museums, exhibitions, and theaters all over the world without leaving the classroom. In-person patient care applications in operating rooms, clinics, hospital wards, and medical training settings. Mixed reality speeds up diagnoses, increases access to healthcare facilities, cuts down on infection transmissions, and improves medical care outcomes. XR enables holographic overlaying of images and data onto real-life situations such as surgical operations, remote consultation, and treatment, opening new avenues in healthcare. In cardiology, initial XR healthcare applications created interactive visualizations that enabled pediatric cardiologists to virtually demonstrate complex congenital heart problems to their students and patients. XR techniques reduce the time required to diagnose cardiology issues, and surgeons who use Microsoft HoloLens headsets during procedures can interact with the hologram using hand movements and benefit from a wider field of view, which improves surgical outcomes. In one application, XR technology enables surgeons to see patients, 3D computed tomography, CT, and magnetic resonance imaging, MRI, scans directly. This will make it easier for surgeons to identify the exact area of the patient's body that needs surgery. This could be especially beneficial for emergency surgeries that must be performed as quickly as possible to save a patient's life. Preoperative simulations are made easier with XR, which creates customized 3D models for each patient and visualizes the inside anatomy in a fully immersive environment. In complex surgical operations, such as reconstructive surgeries, holographic overlays can substantially help surgeons examine the bones and determine the flow of blood arteries. XR may also be helpful for pain relief. In Denmark, Aalborg University researchers studied the potential of XR to provide pain relief for phantom limbs. It may be possible to delude the brain of a person with an amputation into thinking it still controls their missing limb, which may assist in reducing the agony associated with phantom limbs. Telemedicine using XR headsets and 3D XR, medical practitioners are able to review patient histories vocally, discuss with medical specialists, and record patient records. XR-powered headsets can eliminate the need for doctors to review written reports, analyze patient data, and deliver findings in real time, resulting in faster and more precise diagnostics. XR may also provide paramedics with remote support to address emergencies. With XR, paramedics can remotely get support from senior medical professionals. This can help them make more accurate and faster medical decisions, efficiently provide emergency medical aid, and improve patient outcomes. Lastly, XR can help provide remote care to patients with mobility issues. It can also visually project simulations for different situations, offer ease of access to facilitators remotely, increase patient engagement by providing a safe and controlled immersive environment, and leverage telehealth appointments. Therapeutic and mental health applications. The Autism Glass Project at Stanford University's Medical School used XR to help children with autism manage their emotions and identify related facial expressions. There are many other possible applications of the same technology, including the use of VR psychotherapy to address mental health conditions and disorders, and treat the cause rather than the effect of such disorders by combining VR technology with big data analytics. Cloud computing, machine learning, IoT, and blockchain. Effective interaction through wearable computing and cloud technology, AIWAC. Technology provides a full-stack solution aiming at effective, remote emotional healthcare assistance. The solution components allow collaborative data collection, via wearable devices, enhanced sentiment analysis and forecasting models, and controllable affective interactions. Other applications of XR technology as the metaverse evolves. XR-driven technology may be applied in various industries for uses such as the following: equipment assembly, maintenance, and repair engineering and architectural design, e.g., experiencing a virtual building before it is built, market research, e.g., experiencing a virtual product that does not yet exist, entertainment, e.g., cinema, music, and sports, product advertising and promotion. Computer games mixed reality technology also has the capacity to promote social good. For example, applications that combine XR with other innovative technologies to support people with disabilities have already been developed, including technology that alerts people who are blind when rapidly moving objects are headed in their direction. Link to Learning. Microsoft offers mixed reality guidance and allows users to try the technology for free to learn how it can improve workplace processes. According to Microsoft, mixed reality technology can help solve problems while improving productivity and maximizing efficiency. For example, companies such as PCL Construction have successfully utilized Microsoft mixed reality, including HoloLens and Dynamics 365 guides, to enhance project management and on-site operations. PCL visualized 3D blueprints directly on-site and provided interactive training through mixed reality, resulting in improved project accuracy, a 30% reduction in completion times, and a 25% decrease in costs. The technology also enhanced safety protocols, ensuring compliance and minimizing on-site accidents. You can read more about PCL's experience with mixed reality technology and explore other examples. Evolving considerations for standards and guidelines. The use of immersive applications in the metaverse has made it necessary to update the standards and guidelines used to develop applications. Traditional usability guidelines were designed for web and mobile applications that forced users to access applications with computers. Immersive applications force designers to understand how human beings sense things, reason, and plan actions, as well as what motivates people to use available solutions. Designing for these applications requires paying attention to usability, accessibility, and inclusion. The process of designing products to be effective, efficient, and satisfying is called usability. Per the World Wide Web Consortium, W3C standards, it also calls for accessibility and inclusion. It subsumes solution qualities, e.g., effectiveness, efficiency, that are appealing to humans and motivate the use of such solutions. The concept of accessibility addresses discriminatory aspects related to equivalent user experience for people with disabilities. It pertains to solution qualities that make these solutions usable by people with disabilities. For example, web pages that display pictures should have alt text, HTML tags associated with the pictures that can be used to read what the pictures contain, so that people who are blind can navigate to pages and understand what is displayed within pictures they cannot see. In general, people with disabilities should be able to perceive, understand, navigate, interact, and leverage websites and related tools in much the same way as all people do. The concept of inclusion ensures that diverse communities can make use of solutions regardless of their location, culture, and other differentiating traits, habits, or interests. Link to Learning. Read these current usability guidelines to learn how to create websites that are accessible to everyone. Accessibility, usability, and inclusion are important concepts. An important aspect of designing applications is human-computer interaction, HCI. The science that studies interactions between people and computers and evaluates whether computers can successfully interact with humans, as illustrated in Figure 13. 16. HCI is concerned with understanding the influence technology has on how people think, value, feel, and relate, and using this understanding to inform technology design. One Venn diagram circles of engineering, computer science, psychology, sociology, ethnography, and design overlapping to create HCI. Figure 13. 16. Human-computer interaction. HCI studies the interaction of humans with technology to understand how technology influences human behavior. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. The focus of HCI is to ensure that solutions are usable by humans. Usable solutions should be easy to use as well as effective, safe, efficient, and fun for the user. HCI also focuses on the creation of methods that may be used to measure and otherwise evaluate usability, as well as on the definition of usability guidelines and standards. Applying HCI as part of the design of computing systems requires considering human physical and mental capabilities, e.g., attention, memory, as well as the needs of humans, e.g., functional, emotional, social, as constraints at the same level as machine physical constraints such as processor speed and networking capabilities. A usable system must understand the various roles of humans. This includes the following: humans as sensory processors. Usability results when the system fits within human sensory limits for vision, hearing, touch, smell, and taste. Humans as interpreters predictors. Usability results when the system fits with human knowledge. This includes the ability to process information via perception and cognitive processes, such as selective attention, learning, problem-solving, and language processing. Humans as actors in environments. Usability results when the system fits within task and social contexts, such as gender and ethnic backgrounds. Link to Learning HCI guidelines are an important tool to ensure that technology is user-friendly, as well as efficient and accessible. Human-computer interaction. HCI guidelines for immersive solutions. The most important solution development steps in HCI are to define the context. This includes the type of uses and applications, such as industrial, commercial, and exploratory, as well as the market and the customer. The context is not the specific local environment, but rather the larger type of world that the system needs to exist in. This includes the users, physical attributes, physical workspaces, perceptual abilities, cognitive abilities, personality and social traits, cultural and international diversity, and special abilities or disabilities. It also includes task analysis to understand what users need and want to do with technology. Other steps involve function allocation, system layout, basic design, mock-ups and prototypes, usability testing, iterative testing and redesign, and update and maintenance. Similar to mobile solutions, immersive products must go through a series of prototypes to ensure stabilization, feasibility, a single logic path. Alpha prototype, minimum viable product, beta prototype, largely complete, and release candidate, all required functionality ready for product owner review. Quality measurement checklists and design best practices are different for web, mobile, and immersive solutions. Think it through VR accessibility. Ricardo's friends are having fun using virtual reality and avatars to explore castles in Europe. But Ricardo has a disability that prevents him from joining in the fun using the website his friends have selected. Why is this important? How could HCI guidelines help the developers of this website make virtual reality accessible to Ricardo? Super Society Digital Solutions, while Smart Ecosystem Solutions focus on providing insights to their users so they can adapt to change and optimize their activities to guarantee success. Super Society applications go one step beyond by replacing humans in certain mechanical activities and allowing them to focus on activities that machines are not able to perform on their behalf. The set of Super Society capabilities that are being developed keep evolving with capabilities supported by innovative technology components, powered by the hybrid multiclouds that are an inherent part of our evolving web infrastructure. Super Society capabilities. Noteworthy Super Society capabilities being developed today include technology at the molecular level, robotics and advanced robotics, supercomputers, and intelligent autonomous network systems and supersystems. Nanotechnology. The field of nanotechnology focuses on matter at the molecular level to create structures and devices about 1 to 100 nm in size with fundamentally new organization, properties, and performance. Nanotechnology can reduce the size of storage devices available via hybrid multiclouds, making it possible to drastically increase the volume of information available on the web. Some researchers have also suggested a quite futuristic Internet of Thoughts, in which neural nanorobots could be used to connect the neocortex of the human brain, i.e., the smartest conscious part of the brain, to a synthetic neocortex in the cloud. If doable, this could enable the creation of a future global superbrain that would connect networks of individual human brains and AIs to enable collective thought. Challenges associated with nanoscale science and technology include making nanomaterials, e.g., self-assembly, top-down versus bottom-up, characterizing nanostructures, e.g., imaging and measuring small things, understanding properties, nanoland, lies between macroworld and single atoms and molecules, and nanosystems integration and performance, i.e., how we assemble nanostructures into systems. To better understand these challenges, consider Figure 13. 17. Visual representing nanotechnology between natural and synthetic world. Figure 13. 17. Nanotechnology faces many challenges, as matter is used at the molecular level to create structures and devices that are 1 to 100 nm in size with fundamentally new organization, properties, and performance. Attribution, copyright Rice University, OpenStax under CC by 40 license. Credit ruler, modification of the scale of things nanometers and more by NIST. Gov, public domain. Credit top left image. Modification of CSIRO Science Image 11085, a scanning electron micrograph of a female dust mite, by Matt Koloff / Wikimedia Commons, CC by 30. Credit top middle image. Modification of this digitally colorized scanning electron micrograph. SEM revealed some of the ultrastructural morphology displayed by red blood cells by CDC Public Health Image Library, public domain. Credit top right image. Modification of DNA 163,466 by Public Domain Pictures / Wikimedia Commons, CC0. Credit bottom left image. Modification of head of a pin by NIST. Gov, public domain, credit bottom middle image. Modification of model of a MEMS safety switch. Courtesy Sandia National Laboratories, some MIT Trademark Technologies, www. Sandia. Gov / MSDC, credit bottom right image. Modification of carbon nanotube reference materials by NIST. Gov, public domain, robotics and advanced robotics. Robotics and advanced robotics are joint disciplines that include computer science and mechanical and electrical engineering. The field of robotics focuses on the design, development, functioning, and application of robots, as well as the computer systems needed to control the robots, provide sensory feedback, and process information. Swarm robotics emphasizes a large number of robots and promotes scalability. A cyborg is a biological human with parts replaced with machinery, while machines with biological parts added are considered to be an artificial human. Google's Cloud Robotics Core is an open-source platform that facilitates the management of robot fleets, as well as the creation and operation of robotics package solutions that automate business tasks. Other big cloud platforms also provide support for robotics and advanced robotics. Software robots, or bots, e.g., web crawlers, chatbots, are computer programs that operate autonomously to complete a virtual task. They are not physical robots. Instead, they exist only within a computer. Another field of robotics, cognitive robotics, is a field that creates robots that can think, perceive, learn, remember, reason, and interact. It focuses on creating robots that mimic human perception, reasoning, and planning abilities. One subspecialty, biomimetic robotics, focuses on the design of robots that leverage principles common in nature, such as what can be learned from the evolution and development of intelligence in animals and humans. Recent progress and directions in AI, machine learning, and cognitive science drive the focus of the next generation of robotic systems. Figure 13. 18 shows how these areas overlap. Venn diagram with circles for robotics, artificial intelligence, and cognitive and biological sciences converging in cognitive robotics. Figure 13. 18 Cognitive robotics draws from the fields of cognitive and biological sciences and artificial intelligence, as well as robotics. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. The intent of cognitive robotics is to replace humans in dangerous environments or manufacturing processes or resemble humans in cognition, enabling robots to do jobs that are hazardous to people. Cognitive robotics aims to improve robots' perception capabilities as they navigate and manipulate objects in a given environment and interact with people. It also makes it possible for robots to perform tasks by predicting the actions of people around them as well as their own. Cognitive robots can also perceive how people see the world, predict what they need, and anticipate their actions. This explains how these robots can execute daily tasks while interacting safely with people. They are capable of direct interactions, such as assisting customers, as well as indirect interactions, such as sweeping the floor while customers are shopping in a store. Intelligent mobile robots that can move independently were introduced during the Second World War. Following the implementation of artificial intelligence, AI, in robotics, they became autonomous or more intelligent. Figure 13.19 provides a list of components and architecture of modern intelligent robots. Illustration of components and architecture of modern intelligent robots. Figure 13.19 Modern, intelligent robots rely on various components and architecture to function as intended. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Robot Operating System. The Robot Operating System, ROS, is a meta-operating system specially designed for robots. It is open source and supports a variety of services to control robotics hardware, provide hardware abstractions, and perform common tasks. It can also help manage software packages and pass messages from one process to another. ROS also includes various libraries and tools to facilitate the selection, development, and operation of software modules across various computers. Robot manipulators and mobile robots. Characteristics. Robots include robot manipulators and mobile robots. A robot manipulator is a physical tool that operates at a fixed location to catch and move items. A mobile robot is one that can navigate from one position to another. Robot manipulators face the challenge of being able to pick and place objects with a sufficient degree of precision, while mobile robots must be able to estimate relative and absolute robot positions and navigate on a map. Mobile robots are used in applications such as medical treatment, mail delivery, infrastructure inspections, and passenger travel. For example, Now is a humanoid robot that is specially designed to interact with humans. It is loaded with sensors that enable it to mimic emotions. It can recognize people's faces as well as objects and can speak, walk, and dance. Now was created by Aldebaran Robotics, which was acquired by SoftBank in 2015. Sixth generation, Now robots are used in research as well as in the healthcare and education industries. Atlas is one of the most agile robots in existence. It uses whole-body skills to move quickly and balance dynamically. While Atlas can lift and carry objects such as boxes and crates, the robot can also run, jump, and do backflips. Link to learn more about mobile robots by exploring this website about Atlas from Boston Dynamics. Atlas is one of several humanoid robots you can learn about. Zipline is an autonomous fixed-wing aircraft drone used to carry blood and medicine from a distribution center to wherever it is needed. It can launch within minutes and travel in any weather. As these examples show, mobile robots have many applications. Figure 13.20 provides an overview of the fields and industries that find mobile robots useful. Visual showing how mobile robots has a variety of applications in various fields and industries. Figure 13.20 mobile robots have a variety of applications in various fields and industries, including engineering specialties, science, mathematics, and law. Credit, Copyright 2020 Vermessen, Barr, Atella, Serrano, Carlson, Wallstrom, Sand, Ashwitnarian, and Gamba. This is an open access article distributed under the terms of the Creative Commons Attribution License, CC BY. The use, distribution, or reproduction in other forums is permitted, provided the original author, S, and the copyright owner, S, are credited, and that the original publication in this journal is cited, in accordance with accepted academic practice. No use, distribution, or reproduction is permitted, which does not comply with these terms. Computer vision and cognitive robotics. Computer vision advances have facilitated the positioning and navigation of mobile robots. Computer vision is achieved using optics and sensors, which involve image acquisition, image representation, and image processing. Link to learning. The open-source computer vision library. OpenCV is a machine learning software library built to provide a common infrastructure for computer vision applications and to accelerate the use of machine perception in commercial products. Artificial cognitive systems. Robots need artificial cognitive systems that simulate human thought processes to supplement human cognition. Artificial cognitive systems are developed using algorithms in artificial intelligence and technologies such as machine learning, deep learning, speech recognition, and object recognition. Supercomputers. Various supercomputers are being developed based on neuromorphic computing and quantum technology. The supercomputers will eventually be available on the big clouds to help optimize the performance and throughput of super society applications. IBM already provides quantum compute access plans for its cloud, and Intel is building neuromorphic computing hardware that can be leveraged on cloud supercomputers. Cognitive sciences and neuroinformatics. The computing approach that combines the use of AI and cognitive science is called cognitive computing. The study of how to build a computer that can mimic basic human brain functions is called neuroinformatics. This requires robots' ability to handle ambiguity as well as uncertainty. Robots that are equipped with these capabilities can mimic humans' ability to memorize information, learn, reason, react, and show emotions. Table 13. 3 outlines related areas in cognitive sciences and technology support. Subject area brief description, technology support. Artificial intelligence study of cognitive phenomena to implement human intelligence in computers' pattern recognition, robotics, computer vision. Speech processing, learning and memory study of human learning and memory mechanisms to build them on future computers' machine learning, database systems. Memory enhancement, languages and linguistic study of how linguistics and language are learned and acquired, and how to understand novel sentences, language and speech processing. Machine translation, perception and action, study of the ability to take in information via the senses such as vision and hearing. Haptic, olfactory, and gustatory stimuli fall into this domain. Image recognition and understanding, behavioral science, brain imaging, psychology. And anthropology, neuroinformatics, the intersection of neuroscience and information science. Neurocomputers, artificial neural nets, deep learning, aging, disease control. Knowledge engineering, the study of big data analysis, knowledge discovery, and the transformation and creativity process. Data mining, data analytics, knowledge discovery, and system construction. Table 13. 3 cognitive science and technology support. Desired features of cognitive computing systems include the following. Adaptive learning, which is learning as information changes and as goals and requirements evolve, resolving ambiguity and tolerating unpredictability. Interaction with users, allowing users, which may include other processors, devices, and cloud services, as well as people, to define their needs as a cognitive system trainer. Ability to be iterative and stateful, which means the system may remember previous interactions and may redefine a problem by asking questions or finding additional source input if a problem statement is ambiguous or incomplete. Contextual in information discovery, which means the system may understand and extract meaning, syntax, time, location, appropriate domain, regulations, user profiles, process, tasks, and goals, and respond to sensory inputs with visual and gestural effects. The real-world applications of cognitive systems include speech understanding, sentiment analysis, facial recognition, election insights, autonomous driving, and deep learning applications. Deep learning, in particular, requires specific hardware, including graphic processors, digital signal processors, field programmable logic devices, systems on a chip, custom microchips, and application-specific integrated circuits. Some of the providers of deep learning hardware include the Google Neural Machine Translation System, GNMT, Google Cloud's Tensor Processing Unit, TPU, TensorFlow, Cambrican's Neural Processing Unit, NPU, Intel's Movidius Neural Compute Stick, NCS. the Intel Movidius Neural Compute SDK, and Intel's Movidius Vision Processing Unit, VPU. Neuromorphic computing. Cognitive science is interdisciplinary in nature. It covers the areas of psychology, artificial intelligence, neuroscience, and linguistics. It spans many levels of analysis, from low-level machine learning and decision mechanisms to high-level neural circuitry to build brain-modeled computers. It applies software libraries on clouds or supercomputers for machine learning and neuroinformatics studies. It uses representation and algorithms to relate the inputs and outputs of artificial neural computers. It also designs hardware neural chips to implement brain-like computers referred to as neuromorphic computers, as illustrated in Figure 13. 21. Illustration of how human brain with neural network being compared to a computer motherboard. Figure 13. 21. As a field, cognitive science has made many advances, including the design of hardware neural chips, such as those pictured here, which are used to implement brain-like computers known as neuromorphic computers. Attribution: Copyright Rice University, OpenStax, under CC by 40 license. Credit left image: Modification of Artificial Neural Network with Chip by Mike McMarketing/Wikimedia Commons, CC by 2.0. Credit right image: Modification of Amiga 3000T motherboard without annotations by Podstako/Wikimedia Commons, CC0. In 1990, Carver Mead, the Gordon and Betty Moore Professor Emeritus of Engineering and Applied Science for the California Institute of Technology, introduced the term neuromorphic computing, which relies on a hardware architecture that models how the human brain uses neurons. This provides the potential for faster, more complex computations while remaining power efficient. This field of computing emerged to compete with traditional computer architectures. Machine learning became popular, and as it advanced, neuromorphic computing became the best platform for machine learning algorithms. Comprised of a network of neurons and synapses, neuromorphic computing relies on hardware architecture modeled after the human brain. A neuron is a function that operates on an input. A synapse, which processes neuron output and passes a state to another neuron, can be trained to know how to convert neuron output to states. A memristor is a component that remembers the charge of an electric current. Memristors are great for neuromorphic computing as they provide neuroplasticity. Neurons pulse electric signals as input. Output is based on the path taken through the network, and it is a highly connected and parallel architecture that uses side-by-side memory and processing while consuming a low amount of power. Various neuromorphic computing models have been developed on this type of hardware, including the neuroscience-inspired dynamic architecture, NIDA, Dynamic Adaptive Neural Network Arrays, DANNAs, and Memristive Dynamic Adaptive Neural Network Arrays, MR DANNAs. Intel Labs developed the Loihi 2 neuromorphic chip that is used for research along with an open-source framework known as Lava. Intel's goal is to facilitate the adoption of neuromorphic computing. Intel Labs' second-generation neuromorphic research chip, codenamed Loihi 2, and Lava, an open-source software framework, will drive innovation and adoption of neuromorphic computing solutions. Quantum computing. Quantum computing has applications in experimental physics. It provides a theory that is more fundamental than Newtonian mechanics and electromagnetism, and can explain phenomena that these theories cannot tackle. A quantum computer is a machine that performs calculations based on the laws and principles of quantum mechanics, in which the smallest particles of light and matter can be in different places at the same time. Information is stored in a physical medium and manipulated by physical processes. Designs of classical computers are implicitly based in the classical framework for physics and can only deal with bits, not qubits. This classical framework has been replaced by the more powerful framework of quantum mechanics. In a quantum computer, one qubit, a quantum bit, could be both 0 and 1 at the same time. So, as Figure 13.22 shows, with 3 qubits of data, a quantum computer could store all 8 combinations of 0 and 1 simultaneously. That means a 3-qubit quantum computer could potentially process information more efficiently than a classical 3-bit digital computer, depending on the algorithm. Illustration of classical bit 0 and 1, a qubit, and 3 qubits. Figure 13. 22 in a quantum computer, 1 qubit, or quantum bit, could be both 0 and 1 at the same time, enabling a quantum computer to store all 8 combinations of 0 and 1 simultaneously. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Typical personal computers today calculate 64 bits of data at a time. A quantum computer with 64 qubits would be 264 faster, or about 18 billion times faster. A bit of data is represented by a single atom that is in one of two states, denoted by 0 and 1. A single bit of this form is known as a qubit. A physical implementation of a qubit could use the two energy levels of an atom. An excited state represents 1, and a ground state represents 0. A single qubit can be forced into a superposition of the two states, denoted by the addition of the state vectors. Psi greater or equal alpha 0 plus alpha 1, where alpha and alpha are complex numbers, and alpha plus alpha equals 1. A qubit in superposition is in both of the states 1 and 0 at the same time. In general, an n-qubit register can represent the numbers 0 through 2 and 1 simultaneously. Entanglement is the ability of quantum systems to exhibit correlations between states within a superposition. Imagine 2 qubits, each in the state 0, 1, a superposition of the 0 and 1. We can entangle the 2 qubits such that the measurement of 1 qubit is always correlated to the measurement of the other qubit. However, if we attempt to retrieve the values represented within a superposition, the superposition randomly collapses to represent just one of the original values. This means that a wave function changed, and instead of the superposition state continuing, the superposition has collapsed into a single state that has a defined value representing only one of the original values. In the classical computing model, a probabilistic Turing machine, PTM, is an abstract model of the modern classical computer. The strong Church-Turing thesis states that a PTM can efficiently simulate any realistic model of computing, meaning that if a problem is difficult for a PTM, it must also be difficult for any other reasonable computing model. For example, factoring is believed to be hard to perform on a Turing machine or any equivalent model. We do not know whether there is some novel architecture on which factoring is easy. Because we lack certainty, we assume that certain computational problems, such as factoring, possess inherent complexity regardless of the effort put into finding an efficient algorithm. In the early 1980s, Richard Feynman noted that it appeared unlikely for a PTM to efficiently simulate quantum mechanical systems. Because quantum computers operate as quantum mechanical systems, the model of quantum computing appears to challenge the strong Church-Turing thesis. Possible applications of quantum computing include efficient simulations of quantum systems, phase estimation, improved time frequency, and other measurement standards, such as GPS, factoring and discrete logarithms, hidden subgroup problems, and amplitude amplification. Possible implementations of quantum systems include optical photon computers, nuclear magnetic resonance (NMR), ion traps, and solid-state quantum. The optical photon computer operates through the interaction between an atom and a photon inside a resonator, while another approach employs optical devices such as a beam splitter and mirror. NMR represents qubits using the spin of atomic nuclei, with chemical bonds between these spins manipulated by a magnetic field to simulate gates. The spins are initialized by magnetization, and measurement is achieved by detecting induced voltages. Currently, it is believed that NMR will not scale beyond about 20 qubits. However, in 2006, researchers reached a 12 coherent state, showing that scalability up to 12 qubits is feasible using liquid-state nuclear magnetic resonance quantum information processors. Ion traps form qubits using 2 electron orbits of an ion-charged atom confined in a vacuum by an electromagnetic field. Additionally, there are 2 widely recognized solid-state implementations of qubits. A qubit formed through a superconducting circuit using a Josephson junction, which establishes a weak link between 2 superconductors. A Josephson junction consists of 2 superconductors separated by a very thin insulating barrier. A qubit formed using a semiconductor quantum dot, a nanostructure ranging from 10 to several hundred nanometers in size, designed to confine a single electron. Many papers have explored various aspects of quantum computing, including detailed language specifications. For more information about any of the following examples, perform some further research. Quantum Computation Language, QCL by Bernhard Irmer, a C-like syntax and very complete. Quantum Guarded Command Language, QGCL by Paolo Zuliani and others, a high-level imperative language for quantum computing. Quantum C by Stephen Blaha, currently just a specification. Global Issues in Technology, Quantum Computing in Global Operations. Quantum computing is impacting industries throughout the world and improving global operations in fields such as banking, healthcare, manufacturing, and transportation. For example, quantum computing has been used to develop new drugs, design aircraft that are safer and more efficient, provide more robust encryption and online security, and predict the weather with greater accuracy. Quantum computing has the ability to solve problems faster and more effectively compared to classical computing. In 2023, the value of quantum computing's global market size was $885, $4 million USD, and it is expected to increase to $6 billion by 2032, representing a growth of 34.8%. While North America currently holds the largest share of the quantum computing market, other parts of the world, particularly Europe and Asia, are expected to grow over the next few years. Intelligent Autonomous Network Systems and Supersystems. Intelligent Autonomous Network Systems and Supersystems leverage the various supersociety technologies discussed so far. However, one of the missing links appears to be the lack of understanding of what drives human reasoning and planning, which has led to the inability to mimic it to create systems based on artificial general intelligence, AGI. Also, the current approach to deep learning requires using a very large amount of data to train machine learning algorithms and create usable models, which are extremely time-consuming, as well as requiring tremendous resources such as data and processing power. Researchers are striving to come up with solutions to these problems. IANS have the potential to leverage the innovative capabilities of AI, ML, edge computing, and virtualization to offer better human experiences in interconnectivity, compared to automated networks, which have explicitly defined inputs and outputs in predictable environments. Autonomous networks improve operations when functioning in unpredictable environments, with conditions lacking inputs and outputs that can be tested in advance. With IANS, the systems can learn and adapt as conditions change, adjusting to meet whatever needs arise. AGIs are particularly useful in this environment, as they have the ability to work independently, adapting and making adjustments as needed when conditions change. Knowledge management and reuse of processes and information are being looked into as well. A possible approach to facilitate reasoning in the AGI grand scheme consists of using an open-world decentralized hybrid multi-cloud repository that can be accessed by swarm cognitive robots. These robots could reuse, share their knowledge, and adapt their individual behavior in real time according to the context in which they operate.